The given cube is cut into 4 pieces by 2 planes. The first plane is parallel to the face ABCD and passes through the midpoint of edge BG. The second plane passes through the midpoints of AB, AD, HE, and GH. Determine the ratio of the volumes of the smallest and largest of the 4 pieces. So the first thing I have to do is explain this question in detail, and then we'll tackle it. So the first thing we need to illustrate is the diagram. So I'm going to concentrate on this cube and show you how this is being cut. The given cube is cut into 4 pieces by 2 planes. The first plane is parallel to the face ABCD. So that means it is exactly like ABCD, which is right here, ABCD, but it's below ABCD. Where is it? Well, they tell you that. It passes through the midpoint of edge BG. So the midpoint is approximately here. So this is the first cut, like here, all the way across, all right, like that. So that's the first cut, which essentially looks like it cuts the cube in half, with the top half and the bottom half, all right? That's the first cut. The second cut is with a second plane that passes through the midpoints of AB, AD, HE, and GH. So let's draw that, but let's draw that in a different color so you can see what that does. So we're going through the midpoint of AB and AD, so like that. And we're also going through the midpoints of HE and GH, so like that. So hopefully that's drawn pretty accurately. And we're going to slice all the way down. So when you do, you're going to meet the edges like that. All right? So you're making this slice, and then it's going to slice through the diagonal as well. So I hope you can kind of see what's happening here. And if you can't, I'll try my best to explain it further. So this is, first of all, the 2 cuts, all right? The 2 planes. The first plane that I drew in orange was the one that's parallel to ABCD, and the second plane that I drew in red was the one that passes through all the midpoints as given in the question stem, all right? So that is part 1. So that's part 1 right there. Okay, now we get to part 2. If you were to take a side view of this cube, just looking at the side, I'm just looking at the side, and this cut was being made all the way down like this. This cut, that's the first plane, and this is the other plane. This plane, of course, I drew in orange, so I'll draw it in orange over here, like that. There you go. And the other plane I drew in red, so I drew it in red here. This is sort of a side angle. That's how it's being cut into 4 pieces. So it says in the question stem 4 pieces. So we'll label this S, L for small and large, because that's how they label it. And the other 2 are exactly the same. This is also S and this is also L. All right? So I hope you're convinced of that. All right, so here we go. Now we're at step number 3 of this question. Now, when you take the first plane that I've drawn in orange and you cut the cube, essentially you sliced it in half, what is the volume now? Well, the volume is length times width times height, correct? Well, the question tells you that the given cube does it give you any dimensions? The given cube is cut into 4 pieces by 2 planes. First plane, second plane. No, it doesn't. So it's okay. We can introduce some simple numbers. Let's just say 2. Let's say the edge of the cube is 2. All right? Like that. No problem. That's perfectly allowable because in the end they want us to figure out the ratio. So what we call it, it won't matter. So now I want to figure out the volume of not the full cube, but just the half of it. Just that part there. So if I were to draw a 3D, it would be like this. My cube's been sliced in half. So this is 2, but this is now 1, right? And this little chopped section that I drew represents the bottom half. And therefore that volume should be pretty easy to figure out. 2 times 2 times 1. So that's 4. So that means if you're looking at this, that L plus S is equal to 4. All right, the large piece and the small piece are equal to 4. That's very important. That's going to come back later in the question. And before we proceed, let's not forget what we're trying to figure out. Determine the ratio of the volumes of the smallest and largest of the 4 pieces. So they want us to figure out, find S over L, that ratio. All right? You ready for the next step? Okay. Here we go. Now the next step is I have to draw S. This S that I'm trying to figure out, I have to draw it. And once I draw it, I have to then figure out the volume. And then I can use this formula to calculate L, and then I can figure out the ratio. So the next step is to draw S. So here we go. Now before I draw S, I want you to understand that in this one here, this is S and this is S, right? There's 2 S's, but they're both the same. So if I draw this top one, it's like pretty much like I'm drawing the bottom one. And I'm going to draw the top one for you. And I'm going to draw it by using this diagram. And I'm going to draw this diagram again and explain it a little bit better than this plane dissection so that you can understand exactly what S is. So here we go. We have to draw S now. So let's make that second and first plane cut. So the first plane, if you remember, it was just basically cutting the cube in half like this at the midpoint. So that's pretty straightforward. That's probably the easier one to understand. Okay, so the first plane just sliced the cube in half at exactly the midpoint of BG, which is right there. All right, now we have to draw the first cut, or the second plane, which is from the midpoint of AB to AD, the midpoint of GH to HE, like that, and it's essentially going to cut like this all the way across. All right, so I'm just concentrating on the top part, and that top part is going to be my S. So let's see if I can shade it. So this is my top part. That part is my top. This part is my base. And these are my sides. Right there. Okay? That is my shape. That is S. Now, don't worry if you're looking at that and you're thinking, well, what on earth shape is that? I have no idea how to figure out the volume of this. You want me to figure out the volume of S, but I don't know what shape this is. And trust me, I don't know what shape it is either. So what we have to do is we have to make it into a shape. And how do we do that? Well, this is the point of the question that is the key, is you have to extend these lines right here. And if you extend these lines right here, like that, it becomes a, does anybody know what shape this is? This is a tetrahedron. There you go. So it is a tetrahedron. All right? And we can figure out the volume of that. Volume will be 1/3 times the base times the height, h. All right? So here we go. Do we have all the values that we need? Do we have all the values for base and height? Base we do, right? Because this is the base right here. This is the base of this tetrahedron that I've drawn in blue. And we have this part is 2 and that part is 2. They're just sides of the cube. So the base we do, we have 1/3. The base is a triangle, so it would be 1/2 base times height. So 2 times 2, like that. Okay? The height, however, is something we have to figure out. The height of this tetrahedron is this guy right there. How do we figure that out? Well, the good news is that we have a little bit of that information. If we use similar triangles, we can figure out the rest. From the very top till here, right there, I'm going to call x. So this part here, I'm going to call x. And then from here to here, I know that already, and you should too, it's 1, right? Because that first plane cut it at midpoints, so that's 1. And then similarly, from here to here, I know that is also 1. And I know that from here to here is 2, and that's already labeled. So using similar triangles, x over 1, this x over this 1, is equal to the full height top to bottom, which is x plus 1, over this full base, which is 2. All right? And then if you solve for this, you get 2x is equal to x plus 1, and therefore x is equal to 1. Great. Simple number. So now we have the height. The height is the full from the top all the way to the bottom. And that looks like 1 plus 1, so that's 2. So therefore this becomes 8 over 6. And that is the height of the total tetrahedron. But remember, S is not the total tetrahedron. S is just the part that I highlighted in this shaded red. Remember I was doing that? And then I had to add a top to make it a tetrahedron. So if I can subtract that top, this top here that I drew in, if I can subtract that top from the total that I just calculated, then I can figure out S, and we will be in business. All right, so we are almost done. So now this was total, V total. Total volume. And then I just have to figure out now the top volume, which is the part I shaded in green. All right, same formula, 1/3 base times height. 1/3, the base is a triangle. It's 1/2 base times height. It looks like 1 times 1. And we've labeled that in there already. The height we calculated already is 1. So therefore this becomes 1 over 6. So perfect. The volume therefore of S, our S that we are trying to figure out, is the total volume, which is 8 over 6, minus the volume of that top part I shaded in green. And therefore this is 7 over 6. Perfect. We have one final step remaining and we will figure this out. Step 7, or what number are we up to now? Step 4, step 5 actually. Or step, whatever, it doesn't matter. It doesn't matter what step. We'll just call it last step. How's that? I think that's the perfect thing to call it, last step. All right, here we go. So now let's refresh our memory as to what it is that they wanted. They wanted us to find this, right? S over L. And we also know that L plus S is equal to 4. Okay, so they want S over L. And we also figured out that L plus S is equal to 4. All right, great. So this was S, right? So that means L plus 7 over 6 is equal to 4. So L is equal to 4 minus 7 over 6. So this looks like 24 minus 7, 17 over 6. All right? And therefore, finally, S over L, 7 over 6 over 17 over 6. Invert and multiply. And we'll get 6 over 17. And finally, we have 7 over 17. All right? So that is 7 over 17 is 25 is D. Dots with 10 rows and 10 columns is given. Each dot is colored either blue or red. Whenever two dots of the same color are adjacent in the same row or column, they are joined by a line segment of the same color as the dots. If they are adjacent but of different colors, they are then joined by a green line segment. In total, there are 52 dots. There are 2 red dots at the corners with an additional 16 red dots on the edges of the array. The remainder of the dots are inside the array. There are 98 green line segments. The number of blue line segments is... All right, we first need to understand this question. So I'll explain the question first and then we'll try to solve it. Okay, so we've got dots, right? We've got dots that are either blue or red. There's only 2 types of dots, okay? So you got blue dots, like that, and you've got red dots, okay, like that. And then whenever 2 dots of the same color are adjacent in the same row or column, they are joined by a line segment of the same color as the dots. So what that means is that if you have 2 dots, let's say like this, blue and blue, it's so small, I probably prefer to draw it here. Let's say you have 2 dots, they're the same color. They're joined by a line of the same color, okay? And similarly, if you have 2 dots that are red, they'd be joined by a red line, like that, on that array, on that grid. But what if you have 2 dots that are different color? You have a blue dot and you have a red dot. Then it would be joined by a green line segment, like that. And that's what they're saying. Whenever 2 dots of the same color are adjacent in the same row or column, they are joined by a line segment of the same color. All right? Right there. If they are adjacent but of different colors, then they are joined by a green line segment. Okay, so far so good. Let's exaggerate this a bit. Blue, red, okay? Green line segment. Now let's keep going here. In total, there are 52 red dots. Okay, so on this grid, we got 52 red dots. Okay? And I'll write that over here, 52 red dots. There are 2 dots at corners. So at 2 of these corners, there's red. So 2 corners. And then additional 16 dots at the edges. So these are the edges, all right? These are the edges. So we got 16 at the edges. And I'm assuming the and that's exactly what it says. The remainder of the dots are inside the array. So 52 minus 2 minus 16 is 34. So 34 in the interior. Inside the array, interior. You know what? Let's just say inside. I don't want to introduce new terms. We've got enough to worry about in this question. And finally, there are 98 green line segments. So there are 98 of these guys. All right. How many blue line segments? They want you to find how many of these. All right. So hopefully that is a little bit of a explanation. Okay. Now let's start talking about the line segments. How many, first of all, line segments are there? We are told we want to find that how many blue line segments, and they've given us that there's 98 green line segments, and somehow, some way we have to figure out the number of red line segments also, right? But what is the total? The total, green plus blue plus red. Well, look at the graph. It's actually pretty easy to figure out the total, right? I hope. Because you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 on each of those rows, correct? And how many rows do you have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows. So 10 rows, and each has 9 line segments, so 90. Okay, I hope you understand that. There's another 9 right there, and so on. But those are just the ones going horizontal. I've also got to count the ones going top to bottom, vertical. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 that go top to bottom. But in each of these columns, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those columns. So again, 10 columns with each column producing 9 line segments. So another 90. So 90 that go horizontal and 90 that go vertical for a total of 180 line segments. 180 line segments, I'll draw it in black so that you understand, is the total of blue line segments plus red line segments plus green line segments. Okay? That is our mathematical formula. And the good news is that they've given us at least one of these, right? They've given us the value for G right here. It's 98. There are 98 green line segments. So 180 is equal to blue. Let's maintain our theme here. Maintain our colors theme. And plus 98. Okay? So that means that blue plus red is 180 minus 98, which is 82, correct? So far so good, right? I hope you're not lost. Okay. Here we go. So far everything is fine. Don't get overwhelmed. Don't get discouraged. Just take it slow and you'll be able to understand this. Okay, so here we go. Next part of the question, or next part of the explanation, I should say. Now I'm going to concentrate on this guy right here, this information, I should say. They are giving me some important clues. We got 2 at the corners, 6 red dots at the edges, and 34 inside. If you have a red dot at a corner, correct, it will be producing line segments like that. You can look at the graph. I hope that makes sense. If you got a red dot at the corner, it'll produce a line segment going that way and going that way. And that's exactly what I drew over here. Okay? So how many line segments? Well, there was one here and one here. There's 2. For each corner dot, there's 2. But I have 2 corners. So 2 corners two red dots at the corners, and each of those produces 2 line segments. So the total will be 2 times 2, which is 4. Correct? All right. Now let's look at the edges. If you have a red dot at an edge, like this is an edge, right? How many line segments can emanate from it? Well, one going that way, one going that way, and one going down, like that. There'll be 3. So we'll have 1, 2, and 3. 3 line segments that can emerge from each red dot that's on an edge. But we have 16 of them, so 16 times 3 is 48 line segments. I'll write that in there, line segments. All right. Now let's look at the one inside. There's 34 of them inside, so somewhere like here, right? That's inside. And how many line segments can emerge from a red dot inside? One going up, one going down, one going right, and one going left. So there'll be 4 in that kind of form. So if we have a red dot like that, we'll have one going up, one going down, right, one going down, and one going left. So there'll be 4 line segments from each of the 34 inside red dots, and that is 136. So the total line segments, 4 plus 48 plus 136 is 188. Line segments. Okay? Emerging from the red dots. Correct? Now the arrangement is as follows. If you have a line segment that's emanating from a red dot, right? If you have any red dot and you've got a line segment coming out from it, what color is it going to be? Well, if it is connecting 2 red dots, it's going to be a red line segment. If it's connected to a blue dot, it will be a green line segment. So when you have a red dot and a line, that color can only be either red or green, that line segment. You cannot have a blue line segment emerging from a red dot. The only way you can get a blue line segment is if you have 2 blue dots. Correct? So these 188 line segments are either red or green. That's the only way. Well, the good news is we know the question tells us that 98 of them are green. So that means 188 minus 98 is how many red line segments we have. Right? Because we figured out that the total number is 188, and the question tells us that 98 of them are green. So therefore, 188 minus 98, which is 90. 90 red line segments. Okay? Well, that's it. We can now use this equation to figure out blue, because we know that there's 90 red line segments. But if you sub 90 into that equation, you get minus 8 for blue. Blue is, you can't have minus 8, right? So what happened here? This 90 is indeed correct, but we double counted. Why did we double count? And I'll explain that. Let's say you have a red dot here, right, on the grid. The grid is so small, it's hard for me to even show you. And then we've got another red dot immediately below it. And you've got lines, segments emerging. Correct? Now watch. The top red dot, I'm going to draw a line segment going down. The bottom red dot, I'm going to draw a line segment going up. Look at that. That is the same line segment, but it will be counted twice. Do you see how there's two of them? And similarly, you are going to double count like that. That line segment is really just one line segment, but each dot produces it. So therefore, there's actually two that are being included in this total. So the actual number of unique red line segments is 90 divided by 2, like that, which is 45. Okay, so that's a pretty tricky part of the question. Okay, so now at this point we're pretty much done. We have 45 red, and now we can use this equation. We'll just do it right here. We got 82 is blue line segments from red and plus red line segments. So 82 is equal to B plus, we calculated 45, and therefore blue line segments is 82 minus 45, which is equal to 37. So blue line segments is 37. The number of blue line segments is B for question number 25. The lengths of all 6 edges of a tetrahedron are integers. The lengths of 5 of the edges are 14, 20, 40, 52, and 70. The number of possible lengths for the 6th edge is... So here you have some tetrahedrons, and we're looking at it from the top, a bird's eye view. And we are told that our sides are 14, 20, 40, 52, and 70, and they want you to figure out the 6th sides. The 6th edge, the length of that 6th edge. So the first thing I want to mention is that if you have, let's say, a triangle, any triangle like that, there's a fundamental rule that if this is A and this is B and this is C, where C is the longest side length, A plus B has got to be greater than C. Okay? So that's something you probably already know, but it's going to be used repeatedly in this question. So now, let's start with our first tetrahedron and figure out how to place these sides. 14, 20, 40, 52, 70. Okay, well, let's see how I can do this. I'm going to let this side be 70. All right? I don't know, but let's see if it works. And then I'll choose 40 here and 52 here. Now, what's remaining? What sides are remaining? The 14 side and the 20 side. Okay? Now, can I make 14 and 20 go anywhere else, right? That's my dilemma here. Well, first, before I get too ahead of myself, let's look at the triangle right here that I've labeled. Is this legitimate? And we're going to look at that rule. A plus B is greater than C. Well, 40 plus 52 is greater than 70. 52 plus 70 is greater than 40. And 40 plus 70 is greater than 52. So that's perfectly fine. But is it though? That triangle is okay, but I still have to put in these guys. Otherwise, this triangle is of no use to me. By itself, it's fine, but let's see what happens when I put in 14 and 20. All right, let's just put 14 here, 20 here, and see what happens, where 20 is the length of that side, and 14 obviously is the length of that side. Is 14 plus 20 greater than 40? 14 plus 20 is 34. Well, that can't work. I can't have a triangle like that. And therefore, this is no good. So put an X there. I can't make these triangles work with these sides, with this arrangement. So the only arrangement must be that that's 70, that's fine. But I've got to make this 20 and this 52. Okay? That's the only way. Now let's verify that. How about just this triangle right here? Does it match our rules? This fundamental rule up here? Well, 20 plus 52 is indeed greater than 70. 52 plus 70 is indeed greater than 20. And 20 plus 70 is greater than 52. So that is fine. Now, what do we have left? We have a 14 left and we have a 40 left. Correct? Now we have to figure out how to place those. So let's use another set, fresh, right here. 70, 20, and 52. And we've got to place 14 and 40. All right? I'll place 14 here and 40 here, where 40 is that length and 14 is that length. Okay, does this work? 14 plus 40 is greater than 20. Okay, good. 40 plus 20 is greater than 14. 14 plus 20 is 34. It's not greater than 14. 14 plus 20, is it greater than 40? No. So unfortunately, this scenario, again, no good. All right, start again. This one we know is legitimate, so we've got to somehow place 14 and 40. This way of doing it doesn't work. So let's try another way. Let's try 14 here and 40 here. Let's see if that works. So looking at this triangle right here, 14 plus 40, is that greater than 52? Yes, it's 54. 40 plus 52 is definitely greater than 14. And finally, 52 plus 14 is greater than 40. So that works. This is correct. So that means x, that sixth side, the sixth edge that they want us to figure out, must be here, where I placed it. All right? Now, we actually have two scenarios. This is definitely one scenario, but there's another scenario. This is the first scenario, x, 14, 40, 52, 20, and 70. But there's another one. You're just reversing the 40 and the 14, like that. So the 40 would go here, and the 14 would go there. That would still make that triangle completely legitimate with regard to our fundamental rule, that the sum of the two sides have to be greater than the third side. I'll even write that rule again, that A plus B has to be greater than C. All right, using these two triangles, we will now proceed to figure out what x can be. What values can we have for x? And are they integers? Yes, all of them are integers. Okay, here we go. So, in this triangle, we just keep using our rule. We're going to first concentrate, of course, on the x, and that's really all we need to concentrate on. This triangle right here, right there. So in that triangle, the first thing is 14 plus x has to be greater than 20. All right, that's our first rule. 14 plus x has to be greater than 20. Another rule, of course, is that if you look at the entire triangle, like that, we can also get an additional relationship with x, 40, and 70. So that's also going to help us out quite a bit. And I'm going to do that as well, because this one itself won't give me a boundary. I'll see if it does, but I doubt it. X plus 14 is greater than 20. So that means x is greater than 6. All right, x is greater than 6. Whoop. That means it could be anything, right? So we need a boundary. Now, staying with the same side for now, there's another relationship, right? And that is that 14 plus 20 have to be greater than x. This 14 and 20 have to be greater than x. So that means that x is less than 34. So with a little bit of patience, you can see that working with one triangle does indeed give you a boundary. So that's great. We've got x is greater than 6, but less than 34. Okay? Now, before we move on, I hinted at it just briefly, but I'm going to show you again that we also have to consider that triangle right there. Sometimes, you get the right kind of path in a question and you just do it and move on, but pause and see if there's additional ways of making this answer a little more correct than what we think it is. Now let's look at the full triangle, this big one right here. In that triangle, you can see that x plus 40 must be greater than 70, correct? And that 40 plus 70 must be greater than x, like that. So from the first one here, that means that x is greater than 30. And from the second one, we just get x is less than 110. Now we have to combine these two. So that means x is less than 110 and greater than 30. Now what we have to do is combine these two guys. Now how do we do that? Well, if you have a number line, let's say, simplest way to do it I think is a number line. And we've got x, we've got 110 here, we've got 34 here, 30 here, and 6 here. From our first one, x is between 6 and 34. So it's somewhere here. From our next one, x is between 110 and 30. So the common is what we look at. What's common? It's right here. Do you notice how that was common to both? So what's common? The solution of this, if you combine these and these, is x is between 30 and 34. All right? Notice less than, not equal to. So what are our integer solutions? I'll write them in here. X is going to be 31, 32, and 33. Okay, so I hope you understand how that happened. We're going to do the exact same thing on this triangle right here. So hopefully, since I've already done it once, the second time, you can probably do it on your own. So here we go. All right, so first let's concentrate on this triangle right here and see what we get. So from that triangle, we know that x plus 20 has got to be greater than 40. Same rule. And therefore, another condition of that triangle is that 20 plus 40 has to be greater than x. All right, so from the first one, this basically means that x is greater than 20, like that. And from this one, we'll get that x is less than 60. So if you combine these two, x, the boundaries are greater than 20 and less than 60. Okay, so that's our first. Now we have to look at the big one, the full triangle. From that one, you'll see that x plus 14 has to be greater than 70. And another way of looking at it is that 70 plus 14 has to be greater than x. From the first one, you'll get x is greater than 56. And from the second one, you'll get that x is less than 84. So combining these two, x is basically greater than 56, but less than 84. So these are our two solutions. And we have to combine them now. So very similarly, I put them on a number line. And let's start labeling our number line. Our upper limit is 84. Our lower limit is 20. And then we've got the numbers 56 and 60. All right. So let's look at this. From the first one, x is between 60 and 20. So it's this orange zone. From the next one, we've got a scenario that x is between 84 and 56. So 84 and 56, like that. So the common zone to both of these is right here. X is between 56 and 60. So that means that x is equal to 57, 58, and 59. Notice it's less than, not less than or equal to. So there you go. We've got more solutions. 57, 58, 59, and we had up here 31, 32, 33. So how many possible x's did we find? Well, down here we found 1, 2, 3. And up there we found another 3. So 4, 5, 6. 6 possible solutions for x that make the tetrahedron have 6 edges that are all integers. So number 25, the answer is 6, which would be choice E. 1, 4, n has the property that when any two distinct elements are chosen and 2, 1, 1, 2 is added to their product, the result is a perfect square. If n is a positive integer, the number of possible values for n is. So let's first understand this question. We've got 1, 4, and n in a set, and we are going to take any two of them and add 2, 1, 1, 2 to their product. So for example, we take 1 and 4, multiply them, so 1 times 4, then add 2, 1, 1, 2, and that becomes a perfect square. So what is 1 times 4 plus 2, 1, 1, 2? It actually is 46 squared. So there you go, that's the first one. Great. But we have to do, there's 2 more, 1 in n and 4 in n. Take any two elements, multiply them together, add 2, 1, 1, 2, and that's going to be some perfect square. And same thing with 4 and n, 4 times n, add 2, 1, 1, 2, and that will be a perfect square. Okay? And c and b, these numbers, b and c are integers obviously, but it's important to write that down. And also, just from the nature of it, c is greater than b. Okay? So now let's move forward with this. This is the first part. We have to somehow get c and b together in some equation. And I can definitely do that. Let's see here. So c squared is equal to 2, 1, 1, 2 plus 4n. But from this guy, we can get n isolated by itself. N is going to be b squared minus 2, 1, 1, 2. So I'll put that into here. So I get 2, 1, 1, 2 plus 4. N is b squared minus 2, 1, 1, 2. And there you go. I've got c and b in the same equation. I'll simplify this a little bit. C squared is equal to 2, 1, 1, 2 plus 4b squared minus 4 times 2, 1, 1, 2, like that. And let's see here. C squared is equal to 4b squared minus 3 times 2, 1, 1, 2. And therefore I'll put the number on one side, 3 times 2, 1, 1, 2, 4b squared minus c squared. And I think that's about as far as we can go. We can factor this. Perhaps that will help. 2b, 2b, c and c, minus plus. And then this number that we have, 3 times 2112, is there anything unique about it? Does it help us in any way? Well, I don't know at this point, but what I will do is I'll break it up into its prime factors. So 3 is already prime, and then 2112 is divisible by 11, and then that leaves me with 192. So 192 is divisible by 64, I believe. And 64 is 2 to the power of 6, and then you get just 1 out of the 3 like that. Yeah, that's pretty much the prime factor of 2112. So I'll just write it a little bit neater. 2 to the power of 6, 3 to the power of 2, and an 11 like that is 2b minus c and 2b plus c. Okay? Now before we move forward, let's remind ourselves what it is we're trying to find. We're trying to find n, right? The value of n. And n is basically, we isolated it as follows. It's b squared minus 2112. So we have to sort of figure out values for b here. Or values for c, because c is also an equation involving n. If we can figure out the value of b and c, we'll be able to figure out values of n. All right, so just wanted to go back and make that clear. Well, okay, we're getting somewhere here. We have b's and c's, and we've got it into its prime factors. So we've got some choices here. But I don't like the fact that each of these has 2 variables. So I'm going to make them a and b like that. It's going to be easier that way. Okay? So on the side here, I'm going to try my best to get a little bit better of a system. If I'm letting a equal to 2b minus c, and I'm letting b equal to 2b plus c, I can figure out b and c in terms of the big A and big B. And I think that's going to help me in terms of figuring out, are they odd, even, and are they divisible by 2, are they divisible by 4? It's going to give me some clues. So the first thing, I can add these. So that would be a plus b would be 4b. And that means b is a plus b over 4. All right? That helps, right? Because that means b is divisible by 4. Okay, that's fine. Let me just get as much information as possible before I summarize it. Now I'm going to take these two guys and I'll subtract them, try to isolate for c. So b minus a would be c minus c like that, and the two b's would cancel. So b minus a would be basically 2c, and therefore c would be b minus a over 2. So that means b minus a is divisible by 2. Okay, so we're getting somewhere here. So first, let me just write this out like that, and then I've substituted a and b. Now, what have I learned from doing this? Well, one thing, before I even turn my attention to this, is that a times b, that's even. How do I know that? Because 2 is one of the factors. So 2 times something is going to be equal to AB. So AB is even. That's the first thing. The next thing I notice is that right here, B minus A divided by 2 is equal to C, right? And C and B are integers. We made that clear in the earlier part of the question. So that means if B minus A over 2 is an integer, both A and B are even. That's the only way that would be an integer. If both B and A are even, B minus A over 2 would be an integer. Otherwise it would not be. It would be like 0.5 or something. Now I'm going to turn my attention to this and mention something that I think I briefly mentioned before. A plus B divided by 4 is equal to B. That means B is a integer, which we already know. But that means that A plus B over 4 is an integer, and A and B are both divisible by 4. And that's the only way A plus B over 4 could be an integer, which in our case is B. So since A and B are both divisible by 4, I can put for A 4x, and for B I can put 4y. Perfectly fine, since both A and B we know are divisible by 4 according to that equation. So this now becomes 2 to the power of 6, 3 to the power of 2 times 11. 4 times 4 is 16, which is 2 to the power of 4. And then you just get x times y. 2 to the power of 6, 3 to the power of 2 times 11. And the 2 to the power of 4s you can divide both sides by, which leaves 2 to the power of 2 times 3 to the power of 2 times 11 is x times y. This will help us solve for x and y. We can then solve for b and c, and therefore we will get our values for n. Now remember, n is what we're trying to figure out. And n we had earlier a couple forms right here, right? We had one form where n was b squared minus 2112, and we had 4n plus 2112 is equal to c squared. So we can use either of these. I'll use this one here. It looks simpler. B squared minus 2112. So we had n is equal to b squared minus 2112. Now b, we figured out here, is a plus b, a plus large B over 4, all squared, minus 2112. And then a, we call that 4x, right here. And b we called 4y. So we got 4x plus 4y, all over 4, squared, minus 2112. And then the 4's cancel, so all you're left with is just x plus y squared minus 2112 is equal to n. So now we can finally proceed with the table here. We can put x, y, and n. So here we go. X, y, and n. Using this formula right here and using this formula. So if x times y is equal to 2 squared times 3 squared times 11, well, what is that, by the way? The full number is 396. So what are possibilities? Well, we can have 396 for x and 1 for y. We can have 198 and 2. We can have 132 and 3. 99 and 4. We can have 66 and 6. 44 and 9. 36 and 11. 33 and 12. And 22 and 18. These are possibilities where x and y are integers. And then therefore, if you take these values and plug them into this equation, you will get the values for n. And you'll get the following values: 1, 5, 5, 497, 37,888, 16113, 8497, 3072, 697, 97, minus 87, and minus 512. But n was positive. N had to be a positive number, so we can't use these guys. So how many did we get? We got 1, 2, 3, 4, 5, 6, 7. 7 values of n that are positive. So going back to the beginning, if n is a positive integer, the number of possible values for n is 7. So therefore, number 25. A steel cube has edges of length 3 and a cone has a diameter of 8 centimeters and a height of 24 centimeters. The cube is placed in the cone so that one of its interior diagonals coincides with the axis of the cone. What is the distance in centimeters between the vertex of the cone and the closest vertex of the cube? The first thing, of course, is I'm going to elaborate on this diagram right here that they have given in the question. So here is the diagram. Basically, there's this cube that's been placed inside this cone. And the hardest part, of course, is the visualization of how is this going to work. So I'll try my best to explain it in steps. And I'm going to first label these points right here. This one, that I drew the small red dot, that one, and that one. Now those are, of course, vertices of the cube. Now those three in particular are very important. Why? Because those three touch the cone. Okay, I want you to visualize that. Now this one and this one, that's pretty obvious. You can see, oh yeah, no problem. Those touch the cone. But this one touches the cone also, but facing you. See what I mean? So that's the first thing that you have to understand in this question. And then the next part is I'm going to join those three dots that I just drew. And when I join those three dots, I want you to be convinced that those three dots form a triangle that is equilateral and is on the same plane. How do I know that it's equilateral? Because look at the sides. Each side represents what? It represents the diagonal of one of the faces, correct? You can clearly see that. And therefore, since each side represents the diagonal of one of the faces, all three sides are the same. And now I will label the vertices. I'll call this A, I will call this one B, and I'll call this one C. And later, I will of course work with the rest of the vertices, but I'll just label this one here that's at the very top G, and this one here F. Okay? So that is my step 1. Step 2 is something I just touched on, and that is this triangle that I've drawn between A, B, and C. I will draw that next, but I'll draw it from a bird's eye view, completely as if you're looking down on it. So here's that triangle again, A here, B here, and C here. But this is a bird's eye view. Now I want you to be convinced that each of these sides is the length of a diagonal of one of the faces, and I'll call that D. So this is D, that's D, and that's D. Now how do I figure out the length of the diagonal of one of the faces? Well, that shouldn't be a problem. Just draw one of the faces on the side here, and then draw a diagonal, and use Pythagoras, correct? The question tells you that the cube has side length of 3. So this is 3 and this is 3. So figuring out the diagonal is just Pythagoras. So that's 3 squared plus 3 squared is equal to D squared. And therefore this is 9 plus 9 is equal to D squared, which is 18. And therefore D will be the square root of 18, which is 3 root 2. All right, so I'll put 3 root 2 right there. And please remember that these three, A, B, and C, are the vertices of the cube that touch the inside of the cone. Okay, now that we have that established, let's move on to our next part, part number 4. Part number 4 is using this diagram right here, but understanding that this is a cone. So you remember at the top of the cone, you have this circle. right? Just like any cone, the top of it, an ice cream cone, for example, will be in the shape of a circle. Now, of course, in my diagram, it looks like an oval, but that's just because of the way it's been drawn. But if you look at it from a bird's eye view, it will be a circle. Very similarly, since A, B, and C are on the same plane, if you made a cross-section, they would be part of a circle. Like that. So that is the next diagram I'm going to draw. So there you go. There's our diagram again. This is A, this is B, and this is C. Now what I'm going to do is I'm going to draw perpendiculars from each vertex to the other side. So from C, I'll draw one like that. From A, I'll draw one. And from B, I will draw one like this. Now I want you to pay close attention to this line right here. From the center to B. That represents the radius of that circle. Okay? From there to there. And the radius of that circle is going to be very important. Now we can figure that out pretty easily. We know the distance from here to here is D, right there. And D we figured out was 3 root 2. Now, if this whole distance is 3 root 2, then the distance from here to here is 3 root 2 over 2. Why? Because that perpendicular will cut that side in half. Now, how do we figure out R? Well, we take into consideration that this is a right triangle, and since this is an equilateral triangle, each of these are 60 degrees, and therefore this one, if you cut it in half, would be 30, and therefore that's 60. And that is a 60, 30, 90 triangle. So if you have a 60, 30, 90 triangle, the ratio of the sides are 1, 2, and root 3. So since we have one side as 3 root 2 over 2, we can figure out R. R over 3 root 2 over 2 is equal to the ratio, which is 2 over root 3. So that means root 3 times R is equal to 3 root 2, and therefore R is equal to 3 root 2 over root 3. And if you rationalize the denominator, you will get root 6 for R. So that takes care of that step. Now the next step is I want to draw the entire figure once more, concentrating on what we have already discovered. So let's label some points now. At the very top is going to be G, and this is going to be C right here. This I will label just O, and then at the very bottom here I'll just draw a red dot to represent that these two are going to represent a height, and I'll call that H. Okay, and then finally I'm going to label the other vertice of the cube right here, and I'll call that F. And finally this height here I'll call small h. And remember, just in case you're wondering what is G, F, and C, G, F, C right there, those represent vertices of our cube. Here's G, here's F, and here's C. Okay? So now we have to use similar triangles to figure out the relationship between our H and our r that we figured out right here. And remember in the question they told you that the diameter is 8 and the height is 24 of that cone. So that means that this is 8 from there to there. And from there to there, therefore, is 4. And this whole height from top to bottom is 24. So I'll put that on the side there. And then we're going to use these triangles, the big one and this one right here, to figure out a relationship between the height and r. So from the big one, we have 4 over 24 is equal to r, which is right here, the distance from O to C, over h. So this gives me 1/6. R I figured out over here was root 6. And therefore h is equal to 6 root 6. Now we get to our next step, is concentrating now on the distance from G to F, right there. Now G to F, they have actually told you in the opening stem, it represents a diagonal between two vertices on the big cube. The cube is placed in the cone so that one of its interior diagonals coincides with the axis of the cone. And what that means is that the distance from G to F is one of the interior diagonals. So we have to figure out the length of that. So here is my cube, and G is here, this vertice, and F is down here. Okay? So that diagonal between G and F is what is the value for D. That is what coincides with the axis of the cone. So to figure this out, it's a two-step process. First, I've got to figure out the diagonal of one of the faces, and then I can figure out the diagonal of the entire cube. So they gave us that the cube has side lengths of 3. So this initial D, I have actually already figured that out up here. 3 root 2. So, no problem. D is equal to 3 root 2. And then now I've got to figure out GF. Well, this side is 3 because it's just one of the sides of the cube. And therefore GF squared is equal to 3 squared plus 3 root 2 squared, like that. And therefore GF squared is equal to 9 plus 18, that's 27, and therefore GF is the square root of 27, which is 3 root 3. Okay? And now we are getting to the conclusion of this question. Since we have the value for GF, we now have to figure out the value for GO. If we do, we can subtract that from GF. That will give me OF. And then I can then subtract OF from H to figure out my small h, which is the distance from the vertice of the cone to the closest vertice of the cube, which is F. So here we go. The next step is to figure out the value for OG right here. And to do that, I will draw a line from G to C like that, creating a right triangle. And that gives me that OG squared plus R squared, which is OC, from there to there, is equal to GC squared. OG squared plus R squared. R we figured out earlier was root 6. And GC, well, what is GC? GC, if you look at this original diagram, is just the distance from one vertice to another on one face. So it's the diagonal of one face. The diagonal of one face, we figured out right here, is equal to 3 root 2. So GC is 3 root 2 all squared, like that. So this gives me OG squared is equal to 3 root 2 squared, which is 9 times 2, which is 18, minus root 6 squared, which is 6. And therefore OG squared is equal to 12. And therefore the root of that is 2 root 3. Okay? And then now we have to figure out the value for F to O. Okay, no problem. F to O is equal to basically GF, this whole distance, minus GO. So that's GF minus GO, or OG, same thing. GF we calculated over here was 3 root 3 minus 2 root 3, and that is just root 3. And now our final step is to figure out this small h. Small h is just big H minus FO, and that would be 6 root 6 minus root 3. And just to recap, what is exactly the definition for small h? It is the distance between the vertex of the cone and the closest vertex of the cube. And that we calculated to be 6 root 6 minus 3. And therefore, number 25, the answer is A. A triline is a line with the property that 3 times its slope is equal to the sum of its x-intercept and y-intercept. For how many integers q with 1 less than or equal to q less than or equal to 10,000 is there at least one positive integer, p, so that there is exactly one triline through PQ. So all lines are of the form y equals mx plus b. And how do we find the slope? Well, the slope is right there. It's m. And they tell you that 3 times the slope is equal to the sum of the x-intercept plus the y-intercept. So let's figure out the x-intercept and the y-intercept. To get the x-intercept, of course, you set y equal to 0. So that would mean 0 is equal to mx plus b. And therefore, mx equals minus b. X is equal to minus b over m. This is my x-intercept. So minus b over m. And now the y-intercept I will get by setting x equal to 0. And therefore, y is just going to be x, which is 0, times m plus b, and therefore y is b. That's my y-intercept. So there you go. This is my formula. And if I take that formula and simplify it a little bit, let's see, we got 3m equals minus b over m plus b. Let's add a fraction here, top and bottom by m. And this becomes 3m is equal to mb minus b over m. Multiply the m to the other side, cross multiply, and then factor out the b, you get m minus 1. And therefore b, if you isolate for it, will be 3m squared over m minus 1. All right? So substituting back into there, we have y is equal to mx plus b, which is 3m squared over m minus 1. All right, so that is our equation of the line. Now, they tell you that there's a point PQ that is on this line. So let's substitute that in. We've got Q as our value for Y, and we have P as our value for X, plus 3m squared over m minus 1. All right, so far so good. No tricks, no magic here, just straightforward. Now what I want to do is I want to isolate for P, because they want us to concentrate on trying to figure out P and Q. So I've got to isolate for at least one of those variables. So let's do that. So we've got Q minus 3m squared over m minus 1 is equal to MP. This looks like we can multiply top and bottom by m minus 1 to get this additional. And this will be Q times m minus 1 minus 3m squared all over m minus 1. And I'll just bring this m down here. And there you go. I've isolated for P. Now, they want you to figure out integer values for P. For Q being between 1 and 10,000. So they're saying for all of these integers between 1 and 10,000 inclusive, we want you to figure out values for P that are also positive integers. So how do we do that? Well, since this is an equation, looks like it's most likely a quadratic equation, let's make it into that kind of a form. Because in this form, I don't think it will be that easy to figure out individual values for P. It doesn't give us any real help. Nothing really cancels like I had hoped it would. So no problem. We'll just keep going in another direction here, which is trying to figure out this in the form of a quadratic. Okay, so let's do that. We've got 3m squared plus qm minus q is equal to p times m squared minus m. So this becomes pm squared minus pm minus 3m squared plus qm minus q. And then we have minus 3m squared collecting like terms. Bring everything over. Minus pm squared plus qm plus pm minus q is equal to 0. If I multiply through by -1, I think this will be a little bit better. Pm squared minus qm minus pm plus q is equal to 0. All right, so this looks like a little bit better in terms of a quadratic. So I've got 3 plus p. There's my coefficient in front of m squared. And then in terms of the coefficient in front of m, it looks like it'll be minus q plus p. And then I've got this lone q out front. All right, great. So it's in the form of a quadratic equation. Now, let's go back and read the question a little carefully once more. For how many integers q, with q between 1 and 10,000, is there at least one positive integer p, so that there is exactly one triline through PQ? What does that mean? It means that you want exactly one point PQ going through that line. That's it, just one. And the only way that can happen is if our quadratic equation has only one solution. Not two, but one. Exactly one PQ means that there is only one solution to this quadratic equation. And this occurs when the discriminant equals 0. So what is the discriminant in this quadratic equation? Discriminant is of the form b squared minus 4ac, and we have to set that equal to 0. So using our coefficients in this quadratic, that would be minus q plus p all squared minus 4, 3 plus p times q, and that equals 0. All right, so let's solve for this. We've got q squared plus 2qp plus p squared minus 4q times 3, which would be 12q, and then minus 4 times q times p, which would be minus 4qp, is equal to 0. All right. Let's see if we can collect any like terms here. Q squared 2qp plus p squared, and I'll put the 12q over to the other side because it doesn't seem like it groups well, because this groups perfectly. It just factors into q minus p squared. All right, so I've got q minus p squared equals 12q. And we know that q is between 10,000 and 1. So how do we figure out what are our possible values for q? Well, 12q has to be a perfect square. That's what this side is. The left side is a perfect square. So q minus p squared is a perfect square, obviously, and 12q therefore must be a perfect square. Well, 12 is already equal to 4 times 3, correct? And 4 is already a perfect square. It's 2 squared. So that means we've got 2 squared times 3 times q. So this is already a perfect square, so I've got to now concentrate on this. This has to be a perfect square, this 3 times q. Now how can that happen? It can happen if q is of the form 3 times some perfect square. That would make this entire expression a perfect square. 2 squared times 3 squared times k squared. All right, so that basically means that q must be of the form 3k squared. All right, no problem. Let's go back to this equation or equality. Q, I'm saying, is of the form 3k squared, and that is between 10,000 and 1. Divide everything by 3, and I've got 1/3 is less than or equal to k squared is less than equal to 3 approximately. Take the square root of both sides, and that would give me about 57.7 is greater than or equal to the square root of 1/3. All right, so that means k, since k is an integer, that's the only way we can get q to be an integer. K has to be 1, 2, 3, 4, all the way up until 57. That's the only way. And therefore, for each value of k, you'll get a corresponding value of q. Therefore, q will have 57 values. One value for each of the 57 values of k. So therefore, the answer to number 25 is 57, which is choice B. 3 identical cones each have a radius of 50 and a height of 120. The cones are placed so that their circular bases are touching each other. A sphere is placed so that it rests in the space created by the 3 cones as shown. If the top of the sphere is level with the tops of the cones, then the radius of the sphere is closest to. This diagram illustrates the cones if you're looking at this from the perspective of just their bases, the circular part of the cone. And you'll notice, of course, that they touch each other. And what I'm going to draw is the centers of these circles, and then I'm going to connect them like that. And these circles are all identical, and therefore the distance from the centers are also identical, because this is the radius, and so on, right? So this is an equilateral triangle, and that represents the center of this diagram. Now, one thing that's important to understand is that when you place this sphere in that position, the center of the sphere will line up exactly with the center of this equilateral triangle. And what is the center of an equilateral triangle? Well, it is known as a centroid. And now I'm going to draw the diagram to illustrate what is the centroid, and we then have to figure out the distance from the vertex to that centroid. So here is our equilateral triangle, and the first thing I'm going to do is draw lines from the vertex to the opposite sides, like that. And the centroid is this point right here, that one that I just drew the red dot. And we have to figure out the length of this segment from the vertex to the centroid. So how do we do that? Well, one thing we know that this is most likely a 30, 60, 90 triangle. This is, of course, a right angle. This whole angle was 60 because it's an equilateral triangle. So if I cut it in half, this angle is 30. And therefore, since this angle must be 90 minus 30, it's 60. So it is indeed a 30, 60, 90 triangle. And if I draw that triangle over here, I will be able to illustrate what the distance is from here to here. Well, we know that from here to here is the radius of the cone, and they told us in the question stem that that is equal to 50. So this is 50 in terms of a numerical value. But because we know that in a 30, 60, 90 triangle, the ratio of the sides are 1, 2, and root 3, we can now figure out this side. That side, if I call it x and use the ratios, x over 50 is equal to 2 over root 3. So therefore x is equal to 100 over root 3. So that represents the distance from the vertex of the triangle to the centroid, and that is going to help us later in the question. So now I have to bring in the sphere. So far we've just been discussing the three cones, but remember there's a sphere that has been placed, and now we have to try to figure out the radius of that sphere. So this diagram shows you how that sphere has been placed. Now I have to draw it in 2D and try to figure out the radius of that sphere. So here is my 2D representation. This is the cone, this is the sphere. I'll call this point A. I'll call this point B right here. And then we'll call this, of course, the radius, big R. This is also a radius of the sphere, big R. And this point that is tangent, I'll just call that C. And then top to bottom, this green line represents the height, which is the same as the height of the cone. And if you remember, that height is equal to 120. They give you that in the question stem. All right, now this from there to there represents the radius of the cone. And if you remember, that was 50. Now we come to the point of the question where this value comes in. Remember, 100 over root 3 was the distance from the vertex to the centroid, right here. The distance from the vertex to the centroid. And if you remember, the sphere will align with the centroid, the center of that sphere, will align perfectly with the centroid. And therefore, since this is the sphere, this is the centroid right there. And this is the center of this sphere. Those two will be aligned. They'll be right in the same line top to bottom. And this, of course, represents this point, the center of the cone, the circle part of the cone. So therefore, from here to here is essentially the distance from the vertex of that triangle to the centroid. Let me show you in this diagram. This is the center of that cone. This is also the vertex of that triangle. And if you draw a line from the vertex right here to the centroid right here, that represents this distance from here to here. And I think that is probably the most challenging part about this question. So that distance is 100 over root 3. Okay? Now 100 over root 3 is approximately 57.73. So therefore, this distance from here to here has got to be 57.73 minus 50. So this is approximately 7.73. The distance from there to there. Okay? Now, one important point that needs to be mentioned in this question before I move forward is that you've got two tangents. One is from A to C, right there. That C point is tangent to the circle. And the other one is from A to B. That point B is tangent to the circle. And because AB and AC are both tangent to the sphere, it's really the sphere that we are talking about, AB will be equal to AC. And that is something that we will need to use a little bit later in the question. So now we have to figure out R. So what I would like to do is draw a line from the center of the sphere down to this point right here. And the reason is that's going to help me figure out R. And I will label that distance Y. Okay? And then this is, of course, a tangent point, C. So that means that is a right angle. And this is a perpendicular that we had drawn earlier. So that is a right angle. So now this will be two Pythagorean relationships. So the first one involves this triangle right here. And that will give me the following equation. Y squared is equal to 7.73 squared plus this distance. Well, that distance is the full top to bottom, which is h, minus this radius, minus r, like that, all squared. And that gives me y squared is equal to 59.83 plus h is 120, so it's 120 minus r, all squared. So that's the first equation. The next equation will come from this right triangle right here. And that one will give me y squared is equal to r squared plus this distance right here. And I can call this point D, and therefore we can just call that CD. But what's CD? It will help if I knew the numerical value for CD. That way I can just set these two equations equal to each other and solve for R, and we'll be done. So how do we figure out CD? That's the second last step to this question. Well, let's figure that out. First, we will need to figure out the distance from A to D, that whole distance. And that can be done using Pythagoras, once again, using this triangle. Using that triangle, we have h squared plus this small r squared is equal to AD squared. H, of course, was 120. Small r was 50. And then we have AD squared. Solving, we get AD is equal to 130. All right, so we've got part of that. Now we also know that AC is equal to AB. We figured that out earlier right here. So AD minus AC would give me the numerical value for CD, like that. AD we just figured out was 130. AC is the same as AB. And AB, we know, is from here to here, which is the same as here to here, which is 100 over root 3. So 130 minus AB, which is equal to 100 over root 3, which is 57.73, is equal to CD. So therefore, the numerical value for CD is approximately 72.26. And there we go. We can put that back into this equation, and we'll get y squared equals large r squared, which is the radius of the sphere, plus 72.26 squared. And now we can set this equal to that and solve for r. So 59.83 plus 120 minus r all squared is equal to r squared plus 72.26 all squared. And this will help us solve for the radius of the sphere. So here we go. This becomes 59.83 plus 14400 minus 240r plus r squared is equal to r squared plus 5222.2. The r squareds cancel, and I'm going to put the 240r on this side. And all of these numbers, when combined, give you a value of 9237.63 approximately. And solving for r, you will get a value of 38.49. And this is the numerical value of the radius of the sphere, 38.49. Let's go back and see what are the answer choices. 38.49 is closest to answer D for number 25. How many ordered pairs BG of positive integers with 4 less than or equal to B, less than or equal to G, less than or equal to 2007 are there such that when B black balls and G gold balls are randomly arranged in a row, the probability that the balls on each end have the same color is 1/2. The first thing we need to do in this question is figure out a formula. And once we figure out the formula, then we can use these parameters and figure out how many ordered pairs we can get. Now, to understand the formula, it's best if we start with a small example. Otherwise, the formula will not make any sense. So here we go. Let's say we have the following in terms of B and G. We've got 2B and we've got 3 G's. So basically we have 2 balls that are black and 3 balls that are gold. And I want to figure out how many of them, in terms of an arrangement, have the same color on each end, exactly the way that they are describing in the question. The balls on each end have the same color when they are arranged in a row. Okay, well, that should be pretty straightforward. It's one of these. We have either black on both ends and then 3 balls in the middle, or we have gold on both ends and 3 balls in the middle like that. Okay, that's great, but I need to know how many in terms of a number. How many of these are there? And then I also need to know the entire total number, because I have to, in the end, figure out a probability, and that probability has to equal a half. All right, so first let's figure out the total. The total combinations will be as follows. First, you have 5 balls, right? So from those 5 balls, you have to choose 5 in this row. So, for example, you've got 5 slots. For the first one, you got 5 choices, correct? For the second ball, you've got 4 choices. For the third ball, you got 3, then 2, and then 1. And then, of course, you multiply them all. So this is basically 5 factorial. That is the total number. But this overcounts quite a few. Why? Because they're the same letter. So, for example, if I were to call this B1 and B2, notice B1, B2, GGG is the exact same as B2, B1, GGG. See what I mean? So because of this overcounting, we have to divide this 5 factorial by something. What is that something? Well, how many B's do we have? We've got 2 of them, right? So we have to divide by 2 factorial. How many G's do we have? We have 3. So I have to divide by 3 factorial. So that is how I figure out my total. Just in case you're wondering, this equals 10. So my total is 10. Now, I'm also going to write this in terms of B's and G's. So how did I get this in terms of B's and G's? Well, basically what I did was B plus G factorial all over B factorial times G factorial. There we go. That is the total. And I got a numerical value of 10 just to sort of illustrate how this will work. Now I've got to figure out how many of these guys and how many of these guys. Okay, so let's first start with the top one here. For that one, how do I figure out how many of those in terms of a numerical value? Well, the B here and the B here are fixed, correct? Now I initially started off with 2 B's and 3 G's. So the only possibilities for this is the 3 G's. G, G, and G, like that. So there's really only one possible way of doing that. But the number is great, but I need a formula in terms of B's and G's. I can't just put a 1. Okay, how did I do that? Well, these B's were fixed, right? These 2. So that's a done deal. Now I have to figure out how many combinations can I place in the middle. Well, very similar. How many are there? There's 3. So the combinations will be 3 times 2 times 1 for these guys. And that gives me 6. Now you say, well, there's only one way of putting them like that. How can you possibly get 6? Because, just as before, I have to divide by something. What do I divide by? How many G's do I have? I have 3. So I have to divide also by 3 factorial. And when I do that, this becomes just 1. And that's why it is 1. Okay, that's great, but I've got to get this in terms of a B's and G's. No problem. First, how many G's were there? Well, there's 3, correct? And how many B's were there? There was 2. So I had 5 in total. And from those 5, I subtracted 2 to place on either end. So from b plus g, I have to subtract 2. And I have to take that factorial. That is the top number. And in our case, it worked out to be 3. And that's how we got this 3 times 2 times 1. Now what about the bottom? Well, remember, this overcounts if I just left it like this. I have to divide. Divide by what? What am I placing in the middle? Well, I'm only placing g's. How many are there? There's 3. So I have to divide by 3 factorial. And in this case, that's g factorial. Okay? But I also have to divide by the b's. How many b's were there? There was 2. How many did I place on either end? 2. So I have to write b minus 2 factorial. That is very important. So this is my formula for these guys right here. Now in a very similar way, I have to figure out my formula for that scenario. Same thing. First, let's do it in terms of numbers. We've got a g here and a g here that's fixed. So those two I don't have to worry about. But then I've got these left over. I've got 2 b's and a g. So I've got 2 b's and a g. I can place it like that, b, b, g, or I can place it like b, g, b, or I can place it like g, b, b. So that gives me 3. So my numerical value is 3, but I've got to come up with an explanation for how did I get 3 in terms of b's and g's. Okay, no problem. First, let's do it in terms of numbers. In terms of numbers, how I got that was as follows. I basically did the following. How many, first and foremost, numbers do I have to place in the middle? 3. So it's 3 factorial on top. But then I have to divide because this overcounts. Well, in terms of the b's, how many are there? There's 2, so I have to divide by 2 factorial. And then in terms of g's, how many are there? There's 1. So I have to divide by 1 factorial. And that is how I get a value of 3. Now in terms of b's and g's, how did I get the top number? Well, it was basically b plus g, which in our case was 5, subtract 2. Why? Because I'm putting 2 of them on either end. So the top is b plus g minus 2 factorial. Like that. And then the bottom, remember, the g's, I got to take away 2 of them. So it's g minus 2. That is how many I have left to go in the middle. And then from the b's, I'm not taking away any of them. So it's just a full b factorial. And in our case, there was 2. So that is the formula for this scenario. And there we go. Now, how do I figure out the probability? The probability has to equal half. But in this scenario, what is my probability? Well, how many of these did I get? I got just 1, right? So it's 1. Plus how many of these did I get? I got 3. And what was the total? The total was 10. So the probability of getting a scenario where when you arrange them you have the same color on either end is 4 over 10, which in lowest terms of course is 2 over 5. Now we have to do that in terms of these formulas. And when we do, it has to equal a half. So that's the setup of the question. So let's write that in. We've got b plus g minus 2 factorial all over g factorial times b minus 2 factorial. And we have to add this to it, just like how I did numerically. And that's going to be b plus g minus 2 factorial all over g minus 2 factorial times b factorial. And I have to divide all of this by this guy right here. b plus g factorial all over b factorial times g factorial. And that is the equation I have to solve. And this might seem a bit daunting, but the good news is that very quickly a lot of things cancel out. And remember, this has to equal a half. The first step is I have to add this fraction here at the top. And I can do that by breaking up the denominators slightly. So what I did here is basically I took this g factorial and broke it up into g times g minus 1 times g minus 2 factorial. And then in a very similar way, I took this b factorial and broke it up into b minus 1 times b minus 2 factorial. And what that does is allows me to add the fraction. So I'll multiply top and bottom by b times b minus 1 to get a common denominator right here. And multiply top and bottom over here by g and g minus 1 to get a common denominator. And that will allow me to add the fraction. So this now becomes b times b minus 1 times b plus g minus 2 factorial plus g times g minus 1 times b plus g minus 2 factorial. And then the denominator becomes the following: b times b minus 1 times b minus 2 factorial times g minus 1 times g minus 2 factorial, like that. And then don't forget, this is all over b plus g factorial, all over b factorial times g factorial, like that. Now things start to simplify really well. This line right here, I can factor out the b plus g minus 2 factorial since it appears with both terms. And that leaves me with just b times b minus 1 plus g times g minus 1, like that. And then this line right here simplifies very nicely because these three terms combine to give just b factorial. And very similarly, these three terms combine to give me just g factorial. And then of course that is all over b plus g factorial over b factorial g factorial, like that. And let's not forget that this is all equal to a half. It must be equal to a half according to the question. All right, if you invert and multiply, you will get the following. And the good news is this cancels with that. So I hope you noticed that. So now I am just down to one fraction instead of two fractions. And that is the following. Now at this point, the numerator here, or the component of the numerator, and the denominator look very similar. Basically, it's b plus g minus 2 factorial. And on the bottom, I can break this guy up into b plus g minus 1, and then b plus g minus 2 factorial. And if I do that, I can cancel this. And of course, don't forget that term right there. And that, of course, equals a half. So we are almost done with this. That cancels with that, and that just leaves us with the following. So as you can see, I know it was a bit daunting in the beginning, but if you don't make any algebraic mistakes and just kind of go through this, and you have a little bit of knowledge of factorial notation, this isn't really that bad. And at this point, this is just basic algebra. So now we're down to this, cross multiply. And of course, I've got to expand this now. And then I will collect all the like terms and place everything on one side. Now at this point, I'm done with my simplifying and collecting like terms. These three terms, if you combine them, they will basically be b minus g. squared. And that just leaves me with b plus g that I will place on the other side. And this is now our equation that we have to deal with. And keep in mind that our parameters were 4 is less than or equal to b, is less than or equal to g, is less than or equal to 2007. So we have to find all the solutions for these parameters that solve this equation. So how do we do that? Well, notice one thing, that b plus g is equal to something that is a square. So that means that b plus g is a perfect square. So to figure out what are our possible perfect squares, what I'm going to do is look at this set of parameters. First, let's look at our minimum and then our maximum. The smallest possible values of b and g is when they are both equal to 4, right? And that would mean that the sum is 8. The largest possible values of b and g are when they are both equal to 2007, and that would give you a value of 4014. Okay, so I've got to basically look at all the perfect squares in between those two numbers. All right, so this number is right below 9. So it looks like 9 is possibly my first perfect square, and that's 3 squared, of course. This number is a little greater than 63 squared, which is 3939. If I go up to 64 squared, it becomes greater than 4014. So this is the range. It's got to be somewhere in that range. So 4 squared, which is 16, 5 squared, which is 25, of course, and similarly 62 squared, which is 3844, 61 squared, which is 3721, dot, dot, dot. So at first glance, you say, okay, well, we're done. All the perfect squares from 3 to 63, and that looks like there's 61 of those. And is 61 an answer choice? It is. It is choice D. But please don't circle choice D and move on or end the contest, because we have to verify if it will actually work with our parameters. So let's look at the first 3, and then I'll look at the last 3. I think that should be sufficient. So let's start with the first one right here. B plus G is equal to 9. And if that is the case, B minus G all squared is equal to 9. Correct? Going right by that formula right there. So that means that B minus G, if you take the square root, is equal to 3. This equation plus this equation, if I add them, gives me 2B is equal to 12, and therefore B is equal to 6. And if I substitute that back into the first equation, I get G is equal to 3. Does this satisfy my parameters? And the answer is no, because G has to be greater than 4. So this is no good. Now let's look at the next scenario. And that is 16 right here. So in a very similar way, B plus G is now 16. B minus G all squared is 16. So if you take the square root, we get B minus G is equal to 4, and then add the first equation to this equation, and we get 2B is equal to 20, and therefore B is equal to 10. Substitute that back into the first equation, and you get G equal to 6. Does that work? Yes, it does. So we got one. Now, obviously, we're not going to go through all 63 of them, but we just want to see if this pattern kind of continues in our favor, and I'm sure that it will, and so I won't go past this guy. And then very similarly, I want to try from the other end to see if I need to disqualify any of those. So here we go. The next one is 25, so b plus g is 25. B minus g squared is therefore 25, and therefore b minus g is equal to 5. Adding the first equation and the third one, I get 2b is equal to 30, and therefore b is equal to 15. Substituting back into the first equation, I get g equal to 10. So it looks like we'll be fine from this point on. If I do the next one, which is 6 squared, 7 squared, 8 squared, they will all satisfy this parameter. But now I have to do the same for the other end, because the ends will most likely give us perhaps a couple that will be disqualified because they will not fit our parameters. So here we go. Let's try this one right here. So in a very similar way, b plus g is equal to 3939. B minus g squared is equal to 3939. B minus g is therefore equal to 63. First and third equation, if you add them, you get 2b is equal to 4032, and therefore b is equal to 2016. Well, it's not in that range, so therefore we have disqualified one more. So you see the importance of having to calculate at least some of them instead of just circling 61 for the answer. So let's do a couple more, and I think that should be enough. B plus g is now equal to this guy, 3844. B minus g all squared is equal to 3844. And then b minus g, if you take the square root, is equal to 62. Adding the two equations, you get 2b is equal to 3844 plus 62, which is 3906. And therefore b is equal to 1953. And g will be equal to 1891. Are they within our parameters? And the answer is yes. And I think we should be okay with just one more for verification purposes. And here we go. B plus g, this time 3721. B minus g all squared is 3721. B minus g is therefore equal to 61. Adding the first and third, 2b is equal to 3782. And therefore b is equal to 1891, and g will be 1830. Is that within our parameters? And the answer is yes. So there we go. So the verification system that we employed tells us that of these 61, 2 are invalid. So I have to subtract those. And that means the number that are valid in terms of our parameters is 59. So the answer to this very cool question is 59, and that is choice E. A right regular hexagonal prism is sliced as shown in the diagram. The bottom of the new solid is a regular hexagon ABCDEF. The 6 side faces are trapezoids perpendicular to ABCDEF. The top is a hexagon UVWXYZ that is not necessarily a regular hexagon. Of the 6 edges AU, BV, CW, DXEY, and FZ, 3 have lengths 4, 7, and 10. The largest possible value for AU, BV, plus CW, plus DX, plus EY, plus FZ is... This diagram, of course, is the heart of the question, and we will concentrate on this diagram. The first thing, of course, is we have to figure out some sort of relationship. And I'm going to draw a line from U to X right there. And similarly, I'll draw a line from V to Y and Z to W. And sorry, this is not perfectly drawn to scale, but the point is that the very middle point is the midpoint of all of those lines. It's the midpoint of the line from U to X, the midpoint of the line from V to Y, and the midpoint of the line that supposedly is supposed to go from Z to W. It's kind of hard to draw it perfectly because it's on a slant. So that's okay, but you understand. M represents the midpoint of those three lines. Now, I'm going to use a little bit of a notation, don't get confused, that I'm going to talk about the heights. So the height, for example, from the base to U, which is right there, I'll just call the height U, like that. Okay? So for example, this is the height U from here to there. And very similarly, I'll do the same thing for all the other guys. So for example, the height from the base to X is going to be HX, like that. Okay? So let's first just talk about HU and HX. If you add them and divide by 2, you will get the height of M, right? The distance from M to the base. That will basically be the distance of HX and HU divided by 2. Why? Because M represents the midpoint. So I hope you're convinced of that. If you are, we can move forward. Similarly, we can use the other two to figure out HM. And I'll use V, which will be HV from there to there, plus the one that's opposite, which is Y, HY. HV plus HY divided by 2 is also equal to HM. And in a very similar way, HM is also equal to HZ plus HW. So we got HZ plus HW all divided by 2. Okay? So far so good. Hopefully nothing too tricky so far. Now what we do is we just add them. Add them all. And if you do, you get 3HM here. And over here, you get the big long thing divided by 2. And if we, put everything on one side, you get 6HM right there. But then each of these corresponds to each of these, right? I just wrote it like this to help you understand that those are heights. But HU is essentially the same as AU, right? HU is AU. That's basically what it means. I wanted to just illustrate that those were heights. That's why I used H. But then we can convert it back once you understand. And similarly, so that takes care of this guy. HV is BV. And then HW, which is this guy, is CW. And then HX is DX. And then HY is EY. And finally, HZ is the same as FZ. So we basically have exactly what they wanted, and we got it all in terms of HM. So if we can figure out what is HM, we're done. We're done with the question. But finding HM is a little tricky. There's a few cases, and I'll talk about 2 of them, and then you'll see how one gives a value that is the maximum, one gives a value that's not the maximum. So the first one is considering the fact that 3 of them have been given as 4, 7, and 10. All right? So I'm going to do the first one, which in my opinion is the most obvious, which is that AU is equal to 4 and BV is equal to 7 and CW is equal to 10. That's probably the most obvious one. All right, let's figure this out. If this is the case, then we can figure out HM with any of these guys here. Okay? So I can just use, for example, this one right here. So that would mean that HV plus HY over 2 is equal to HM. Well, HV is the same as BV, right? The height from V to the bottom is the same as BV, this guy right here. So BV I've called 7. Well, HY, what is HY though? Well, HY is from there to there, but we don't know that. But because of the way I've labeled it, I'm basically saying that this is the same height as that. Okay? So that if you were to look at it from this angle, that it's not tilted. You see what I mean? Z is on the same level as V, and then Y is on the same level as X. Okay, I hope that makes sense. And therefore, since it's not tilted, that means HY is the same as HW, which is CW. So we get 7 plus 10 over 2 is equal to HM. And therefore, HM is equal to 17 over 2. So therefore, going back into here, 6HM is my value for this whole thing that I have to figure out. So that's 6 times 17 over 2. And that is equal to 51. All right. 51 is one of the answer choices. But is it the largest possible value? Now, that is the tricky part to this question. You don't know. Do you take a chance and circle it? And unfortunately, 51 is not the largest. It is a possible value, but it's not the largest possible value. Okay, so how do we get the largest possible value? Okay. This is where that whole thing about tilting comes in. So if I were to look at it from that angle, it's not completely the same in terms of lengths. Like V to the bottom is not the same as Z to the bottom. It's tilted. So how do I explain that? I'll just draw a little sketch. Before, it was not tilted, right? So if you're looking at it from this point, it would look like this. Here's U, here's V, here's Z. And if you go a little higher up, you would get to Y, and you will get to W. And then, of course, they all meet at X. Correct? But this can be tilted. So it means that instead of these being uniform in terms of its length from the bottom, they could be tilted like this. So if we're making a comparison, now V is here. See what happened there? Top to bottom, V is there, and now Z is here. It's no longer completely uniform so that the distance from the base to V and the distance from the base to Z is the same. And then we've got this sort of scenario here. Does that make sense? Or this is now W, and this is Y, and this is X. So that tilt is very important. And if you do that tilt, you can come up with another scenario. And that other scenario is as follows. This time AU can be shifted to be 7, and then BV can be made to be 4, a little bit shorter, and then CW, we can keep that as 10. All right? So I hope that makes sense. We just shifted it so that we kind of just, what we did was we lowered V down a little bit. Okay? So we have to work with this now. Now I want you to look at MW, which is right here, and compare that to UV, which is right there. Those two are parallel. So I'll write that over here. And because MW is parallel to UV, the height to M, which is basically HM, if you subtract from that the height HW, so basically we're taking this height and subtracting it from that height, it'll be the same as the height U minus the height V, which is this height minus that height. And therefore, using these values that I've just selected by rearranging the numbers a little bit, I can figure out what is HM. HM will therefore be minus HW, which is the same as CW, which is 10. HU is 7, and HV is the same as BV, which is 4. So this gives me HM is equal to 3 plus 10, which is 13. So I take my value of HM equals to 13, and I come back to my original formula and get rid of this guy, because we need to figure out something new. And then I take HM equals to 13 and substitute it. And if I do, I get 78. And that is the largest value that we can get. Interestingly, if you were to look at this diagram, if this is your selection, then the other ones will be 19, 22, and 16. And the way I got that is just by these relationships right here. Not that you really need to, but just to kind of make the question complete. So it's a challenging question. I think the hardest part was the tilt. I'll write that in there. The tilt involving this top face or the top polygon when you look at it from the viewpoint of that direction. So the maximum is 78, and therefore the question 25, the answer is D. In the diagram, 3 circles of radius 10 are tangent to each other and to a plane in 3-dimensional space. Each of the circles is inclined at 45 degrees to the plane. There are 3 points where the circles touch each other. These 3 points lie on a circle parallel to the plane. The radius of the circle is closest to. In this diagram, we have labeled A, B, and C, which you cannot see, and those points represent where the circle touches the plane. And then what we need to do is draw lines that extend like that and contain A, B, and C, but when you connect those lines, they form a triangle, and it is an equilateral triangle where A, B, and C are the midpoints. And we can represent that on this diagram right here, where this is E, and this point right here is F. Now let's look at this diagram. This represents the triangle DET, where this is DET on this diagram, where T represents the top of that pyramid that is drawn. And the circle, which is this one right here, is represented right here. You're looking at it face on. And this diagram is very important because it allows us to figure out the distance from G to H. And G to H will be critical. And what is G and H? Well, G and H and J, labeled there, represent the points where the circles touch each other. And if we can find the distance between 2 of those points, such as GH, that will help us figure out the radius of the circle that encompasses those 3 points. Next, let's concentrate on this diagram a little bit more, so I will blow it up. In this diagram, we will label E here, F here, and then the midpoint approximately here is A. And now we need to join the lines from A to T, like that, and then from A to O, like this. And keep in mind that this is going to be a right angle. It's on a slant, so it's hard to see that it's a right angle, but it is a right angle right there. And if you recall, the circles were tilted 45 degrees. So that means that since the circle is inside DET, as shown here, that circle and that plane that DET represents is tilted 45 degrees. So that means this angle in here is 45 degrees. And therefore this angle right there must also be 45 degrees. So this is a 45, 45, 90 triangle. And the ratio of the sides of a triangle with those angles is 1, 1, and root 2. So that means that if you were to take the ratio of the sides AT to AO, it would be root 2 over 1. So that's very important. Now the next step is concentrating on this triangle right here, DEF. When you look at DEF from a bird's eye view, it will look like this. And all of these points are labeled. And since this was an equilateral triangle, when you draw a line that's perpendicular to the other side, it will cut this 60-degree angle in half. So this becomes 30. This is, of course, a 90-degree angle. And this will be 60 degrees. So the ratio of the sides of a 30, 60, 90 triangle are 1, 2, and root 3. So therefore, we can get a relationship between those sides. In particular, if I label DA to be x, x over AO will be equivalent to root 3 over 1. And similarly, if you rearrange this, AO will be equivalent to x over root 3, like that. Now we use this formula and substitute that into there. And if we do, we get that AT over AO, which is x over root 3, is equivalent to root 2. So AT is equal to root 2 x over root 3. Okay, so now we can use Pythagoras on one of the triangles, and that triangle is right here. ADT, that triangle right there. And if we do, we get the following relationship. We get AD squared plus AT squared is equal to the hypotenuse, and in our case, that is DT squared. And we have numerical values or values with x for each of these. We have the following. For AD, we have labeled that x. AT, we just figured out, was root 2 over root 3 x. And then that is going to be dt squared. So if you do this math here, we get x squared plus 2 over 3x squared is dt squared. And therefore that is going to be 5 over 3 x squared. And then if you take the square root of both sides, you get dt is equal to root 5 over root 3 x. Now that we have that formula, we need to look at an additional diagram, and it's this one right here. This diagram will allow us to figure out the length between two tangent points. And in particular, G to H, where G and H are two of the points that the circles touch at. So in this diagram right here, which represents pretty much the same as previous diagrams, just a few more labeling, R represents the center of that circle, and we've drawn a line directly across from G to H. And we will now use similar triangles to get the following relationships. SG over TG is equal to AD over TD. So the two triangles that we used there were this triangle, the small one, and this triangle, the big one. And this similar triangle relationship gives us the following. SG over TG is equal to AD, which we had previously labeled as x, and TD, or DT, which we just figured out, is 5 over 3 root x. So x's cancel, and all you're left with is the root of 3 over 5 for the relationship of SG over TG. And then we use similar triangles again to get TG over GR is equal to AT over AD. And the two triangles we use to get that relationship are TGR, this triangle, and the big one, ADT. They have the same angles. So from this, we get the following, that TG over GR is equal to AT, which we had previously calculated as root 2 over root 3x, all over AD, which we had previously labeled as just x. So this brings us to just the root of 2/3. So now we can use our findings to figure out the value of TG. Now GR, if you look at this, is the radius of that circle. And in the question stem, they tell you that the radius is equivalent to 10. So that we can put just 10 as our value for GR. So isolating for TG, we get the root of 2 over 3 times 10. And then finally, we can now figure out SG since we know what TG is. SG will be TG times the root of 3 over 5. So that is equivalent to root 2 over root 3 times root 3 over root 5 times 10. The root 3's cancel, and if I rationalize the denominator by multiplying top and bottom by root 5, I will get root 2 times root 5 times 10 over 5, and this of course is just 2 root 10 for SG. And SG represents this distance, so GH will of course just be double that. So now we have arrived at our final step, which is figuring out the radius of that circle at the very top that encompasses the 3 points that the 3 circles touch each other at. And this red circle represents that circle that they are talking about in the question. And this is, of course, the very important final step. What we have to do now is figure out the radius of the circle, and we do that by drawing lines that are perpendicular to opposite sides, and then looking at the fact that this is again an equilateral triangle, and these are 30, 60, 90 triangles. So let's recap here. The distance from G to H is basically the distance between two of the points where those 3 circles touch each other. And we just figured out SG, which is 2 root 10. So the radius, of course, is going to be right here, from here to here. And we can use 30, 60, 90 triangles. So this is 30 degrees, since that's an equilateral triangle, and that angle is 60, but we cut it in half. And then, of course, this angle is 60 degrees. So, as always, the ratio is 1, 2, and root 3. So, finally, the ratio of SG over R is going to be equivalent to root 3 over 2. So that means root 3R is 2SG, and therefore R is equivalent to 2 times SG over root 3. And SG is 2 root 10. So this becomes 4 root 10 over root 3. And that is equivalent to approximately 7.3. So this is a very good question, very challenging, I think, and I encourage you to go over it carefully, looking at these diagrams and trying to understand the three-dimensional aspect of the question. Number 25, therefore, the answer is C. Alex chose positive integers a, b, c, d, e, f and completely multiplied out the polynomial product. After she simplified her result, she discarded any term involving x to any power larger than 6 and was astonished to see that what was left was 1 minus 2x. If a is greater than d plus e plus f, and b is greater than c plus d, and e is greater than c, what value of a did she choose? The first thing in this question is to try to simplify this, and we do that by noticing that there are certain algebraic identities that we can utilize. And these algebraic identities are used to simplify this into a slightly better form as follows. And I encourage you to go through these steps and figure out how we went from the initial given equation all the way to the bottom, which is right here. Basically, you take these algebraic identities and start subbing them in and then collecting like terms, and you will be able to get to this final step. This final step, the simplified version, is what we are going to work with, but we are going to make a few substitutions. This exponent we are going to call A, big A. So A will be A minus D minus E minus F. This exponent we are going to call B. So big B will be equal to B minus C minus D. And in a very similar way, that exponent we will call C, big C, will be E minus little c. And then big D we will call little d. And then just to be consistent, we will call the next one E, and the last one we will call F. Okay? So that means that this equation basically boils down to the following. It becomes 1 minus x to the A, 1 plus x to the B, 1 minus x cubed to the C, 1 minus x to the fourth to the D, 1 minus x to the fifth to the E, and finally 1 minus x to the sixth to the F. Okay? So at this point, we have to use the binomial theorem to expand this. But the good news is that because we are initially going to be looking at values of x squared, because remember, this polynomial, when fully expanded, does not have anything of the form x squared, x3, x4, x5, or x6. So first, we are going to try to concentrate on the fact that there's no x squared when this whole thing is expanded out. So when we expand this using the binomial theorem, we initially only need to do it for the first two terms, because those two terms will give us an x squared, and all of these others won't. So that's why we only have to look at those first two. So first, let's talk a little bit about the binomial theorem. What is its general look? This is the general way that it would expand something using the binomial theorem. If it's 1 plus y, it would look like this. If it's 1 minus y, it would look like this. And the good news is that you only have to concentrate on the first few terms in order to get a x squared. So we will do that on this one right here. And there is our expansion. And we are only considering that we have to look at the x squared. So when you first did the expansion, it looks like this, right? But then when you simplify, it basically just boils down to this when you collect like terms. So the coefficient of x squared is just this guy right here. So that is what we will concentrate on. Now, since there is a term minus 2x and no x squared term in the full expansion, what that basically means is that this is equivalent to minus 2x. So minus a minus b x is equal to minus 2x. So that means a minus b must be equal to 2. And then this whole thing has got to be equal to 0 because there's no x squared term. So that means this, if you multiply it out, it becomes a squared minus a plus b squared minus b minus 2ab is equal to 0. I just multiply through by 2. If you factor this, you can do that. It becomes a minus b squared. And you can put the a and b on the other side. Now, a minus b is 2. So that means a plus b is equal to 2 squared, which is 4. So now I've got a minus b is equal to 2. A plus b is equal to 4. So I can add them. If I add them, I get 2a is equal to 6, and therefore a is 3. So that is my first letter that I have solved. And this one will quickly give me a value for b. B is going to be equal to 1. So I've got a and b so far. And in a very similar way, we're going to get the numerical values for C, D, E, and F. So now that we know a is 3 and b is 1, our polynomial now becomes 1 minus x cubed, 1 plus x to the power of 1. And then all the other ones we still don't know because we have not figured out those letters yet. But we can expand this out since we know these. And when you do, you get the following. 1 minus 2x plus 2x cubed minus x to the power of 4. And the rest remains the same. As we discussed before, we also have no x to the power of 3 in the full expansion. So that means that this x to the power of 3 must eventually cancel somewhere. And that minus 2x to the power of 3, that will cancel the positive 2x to the power of 3, that's got to come from this guy right here, because that's the only one that has x to the power of 3 in it. And therefore, we have to again use the binomial theorem to expand this, but we only have to do it in a way that we get the very first two terms. And if you do it, you will clearly see that the expression becomes 1 minus cx to the third. So that means this minus cx to the third has to be equal to minus 2x to the third in order for that to cancel with this guy, which appears right here. Because remember, the question says that when you do the full expansion, there is no x to the power of 3 term. So this basically means that c is equal to 2. So now we've got another one of those variables. Now, since c is equal to 2, that means my polynomial now becomes, and when you expand it, this is what the polynomial looks like at this point of our question. Now we continue in the very similar way. We have also been told that there's no x to the fourth, x to the fifth, and x to the sixth. And those are the ones that will help us solve for D, E, and F. So There is no x to the fourth in the full expansion, so we have to cancel this 3x to the fourth with a minus 3x to the fourth. And that minus 3x to the fourth has to come from 1 minus x to the fourth to the power of d, because that's the only term that has x to the fourth in it. So again, use the binomial theorem to expand this. And you only need to expand just so you get the first two terms, and that will easily show you that this must be equal to the minus 3x to the fourth. So minus dx to the fourth must be equal to minus 3x to the fourth, and therefore d is equal to 3. So now I have got another variable. So if d is equal to 3, my equation now becomes this right here, which I obtained by putting d equal to 3. Now at this point, again, we have to continue in the same way. We know that there is no x to the 5. So to cancel this 6x to the 5 that I have figured out, there has to be a minus 6x to the 5 that comes from here. And as before, we use the binomial theorem to expand this. And when you do, you get 1 minus x to the fifth plus ... But we don't need to go any further. We just know that this has to be minus 6x to the 5. So that means minus x to the 5 has got to be minus 6x to the 5, and therefore e is equal to 6. So I've got the second last one, and therefore as e is equal to 6, my expression now becomes equal to this. So at this point, we have just one letter remaining to solve. And by this point, hopefully you get the hang of this, that there's no x to the sixth. So this 9x to the sixth must be canceled by a negative 9x to the sixth. That's got to come from there. So, as always, with this question, we have to use the binomial theorem to expand. And when we do, we get 1 minus fx plus ... And then this, therefore, has to be 9x to the sixth. So minus fx to the sixth has to be equal to 9x to the sixth. Therefore, it had to be negative 9x to the sixth. That's what we need to cancel. So therefore, f is equal to 9. So there we go. We've gotten all the letters. And I will summarize all those letters. A we got as 3, B is 1, C is 2, D is 3, E is 6, and F is 9. Now recall, those were the big ones. We had made substitutions earlier. We had made the substitution that big A is equal to small a minus small d minus E minus F. That big B was equal to B minus C minus D. C was equal to small e minus small c. D was equal to just small d. E was equal to F, small f, and big F was equal to small c. So we can quickly get these. Some of these are pretty easy. C, therefore, is going to be equal to F, this small c, A, B, C, D, E, F, these small letters. C is equal to F, well, F is 9. So there we go. E is equal to F, so this small f is the same as big E. And then big D is equal to small d, so D is equal to 3. Now let's figure out E, B, and therefore A, where A is the one that the question is asking for. Well, from this equation right here, big C is equal to E minus C. Well, big C is 2. So 2 is equal to E minus C. And C, small c, is 9. So therefore, small e is 11. And then from this equation right here, our big A is equal to A minus D minus E minus F. Our big A is 3. A is what we're trying to figure out. Small d is 3. Small e is 11. Small f is 6. So therefore, A is equal to 3 plus 20, and therefore A is 23. And that is the answer to the question. So number 25, the answer is E. Side length 20. A right circular cylinder has a diameter of 10 and a length of 10. The cylinder is lying on its side, completely inside the pyramid. The central axis of the cylinder lies parallel to and directly above a diagonal of the pyramid's base. The midpoint of the central axis lies directly above the center of the square base of the pyramid. The smallest possible height of the pyramid is closest to. The key to figuring out this question is to realize that the smallest possible height of the pyramid is obtained when this part of the cylinder is tangent to one of the sides of the pyramid. And I will draw a triangular relationship to illustrate that. This red triangle I just drew is the illustration that helps understand this question. This point right here is the point where that cylinder is tangent to the pyramid. And that will help you figure out this question. So that is step number 1 of this question. And then what we have to do is draw a diagonal from one corner to the other, like that. And that will also help us figure out some of these lengths. So here we go. Let's talk about this now. The length of the square base is 20. So this is 20 from here to here. And so is the length from there to there. It's a square base. Now, because it's a square, that is going to be a right angle. So we can use the Pythagorean theorem to figure out the full diagonal right there. So we'll do it over here. Diagonal squared is going to be 20 squared plus 20 squared. And therefore, diagonal squared is 2 times 20 squared. And therefore, diagonal will be 20 root 2. Now, we are told some very important clues actually in the question, that the center of the square and the center of the cylinder coincide. So let's draw a line from this vertice to the center, so approximately here, where this is the center of the square and also the center of that side of the cylinder. Now they told us that the cylinder is having a length of 10. So from here to here is 10. If this line is the center, that means from here to here is half of that 10, which is 5. So this is 5, so I'll just put a 5 there. Now from here to here is half of that diagonal. Now the diagonal is 20 root 2, so half of that diagonal is obviously 10 root 2. So from here to here is 10 root 2. Therefore, the distance from here to here is 10 root 2 minus this 5. So I'll just put that here. That is going to be 10 root 2 minus 5. Now, in this triangle that I had originally drawn, I am interested in figuring out the sides of that triangle. And one of those sides is this guy right here. So I will use this finding of 10 root 2 minus 5 to figure out this side. And to do that, I will draw a diagram of the square base if you're looking at it from a bird's eye view. And here we go. We got the diagonal, of course, from one end to the other. And then this line right here that I'm interested in, I've got to draw that in here. Now that line in the diagram extends all the way to the other side, right? Like that. So I've got to do the same kind of thing, but in this diagram that I'm showing in a bird's eye view. So it's going to be something like this. And to make this diagram complete, let's draw the other diagonal. And now let's compare. This guy right there is the same as this right here. All right? And that is very important to recognize. Now, this part is the same as this part. So let's label that from here to here is equivalent to 10 root 2 minus 5. Now, what is very interesting about this diagram is that this is a right angle. And since this was a diagonal, this is 45 degrees. And therefore, this must be 45 degrees. So that means this is the same as that. So since those two sides are the same, this is also 10 root 2 minus 5. So there we go. We just got this side. So I'll just draw it here. That is also equal to 10 root 2 minus 5. Now the next part of the question is looking at this circle right here and this triangle like that. So I'm going to draw this triangle containing this circle, which is tangent. But I'm going to draw it so that you're looking at it head on. Right now it's on a slant and it's very difficult to sort of see. But I'm going to draw it face on. So here we go. And there we go. Exactly like that diagram. The only difference is now I'm looking at it head on. And now I have to draw in my relevant lines. So first from top to bottom like this, touching the bottom. And then from the center of the circle to the tangent point. And I think that should be sufficient. Now let's discuss this. This side right here is the same as this side. So let's label that. We know that that is 10 root 2 minus 5. This from here to here is just the radius of that small circle. The question told you that the diameter is 10, so therefore the radius is 5. So that's 5 right there. And the other radius is right here. That's also 5, right? Because that's also the radius. Now the other parts of the diagram we don't really know. Like for example, from here to here, I don't know what that length is, so I'll just call it x for now. And then this top to bottom, I'll call that height. But remember, it's not the height of the pyramid. The height of the pyramid is over here. That's that. I'm going to do that later. This is just the height from here to here. So I'll call that small h. So that the height from there to there, I'll just call it small h. And therefore from here to here is h minus 5. Now these are tangent points, so that means these create right angles, right there and right there. And I'll draw one line segment to illustrate some very important point, that if you have a tangent from a point, this point for example, let's call it P, and it goes right here. If you draw a tangent from that same point to the circle, those two lines will be the same. So this distance is the same as this distance. That's very important to recognize. So that means the distance from here to here is also 10 root 2 minus 5. And the good news is this is going to create for us a similar triangle situation. And it will, believe it or not, solve the question. Let's just label it. I'll call this theta, and therefore this angle in here is 90 minus theta. And you'll see, therefore, that this big triangle will be similar to this smaller triangle because they have the same angles. This angle in here is 90 minus theta, and this, of course, is a right angle. So let's figure out the similar triangle relationship. This, which is x, which is the 90 theta side on the small triangle, will be equivalent to the 90 theta side on the big triangle. And on the big triangle, it's the top to bottom, which is just h. And then the other one I'll look at is this side, which is 5 in the smaller triangle. It is the 90 minus theta 90 side. It will be equivalent to the 90 minus theta 90 side on the big triangle, which is 10 root 2 minus 5. So I've got a very good relationship there, my first one. I can come up with another one, and another one involves the following. Same triangles, but different sides. This side this time, it's the theta and the 90 minus theta side, which gives me h minus 5 in the small triangle. And on the big one, the theta and the 90 minus theta side is that side. So that is actually x plus 10 root 2 minus 5. And then, of course, I'm comparing it. On the small triangle, it's the 90 theta minus 90 side, which is this guy. So that's 5. And on the big triangle, the 90 theta minus 90 side is this side. So that's 10 root 2 minus 5. So there we go. We got two equations, two variables, and now we will use those to solve for h. H is probably going to be the value that's going to help us the most. So here we go. From the first equation, we will get that x is equal to 5h over 10 root 2 minus 5. The 5's cancel, so you're just left with h over 2 root 2 minus 1 for our value for x. And then what we can do is substitute that into here and solve. So instead of x, I'll put h over 2 root 2 minus 1 plus 10 root 2 minus 5 all over 10 root 2 minus 5 is equal to h minus 5 over 5. And let's cross multiply here. If you do, you get 10 root 2 minus 5 just goes over there, and then we can simplify this a little bit. This just becomes 2 root 2 minus 1. And at this point, it's just number crunching because we don't really have a quadratic situation, so we don't have to worry about that. We just have to solve these radicals. Multiply through by this guy, and that will probably help us a little bit. It will get rid of this, and then this becomes 2 root 2 minus 1 times 10 root 2 minus 5. And on this side, it'll be 2 root 2 minus 1 squared, since I'm multiplying the same thing, h minus 5. And at this point, you can expand, but I think it's easier if you convert it to decimals. As long as you use about 2 or 3 decimal places, you should be able to get the accurate answer. So this becomes a 9.14 for that 10 root 2 minus 5. And the 2 root 2 minus 1 is about 1.828. And then on this side, this 2 root 2 minus 1 squared is 3.343. And then, of course, we just have our h minus 5. And then this becomes h plus 16.707. And this is going to become 3.343h minus 16.715. Bring the 16s over, and you get 33.422 approximately. And this is 2.343h. And then divide through, and you'll get the value for h as 14.26. All right, we are just probably a minute away from solving this question. Now we have our value for small h, but we want the value for the big H. So we got our value for small h as 14.26 after all that mathematics. And that small h was this guy right here, top to bottom. But we don't want that. We want the big H. And that big H is represented from the top to the base of the square, which is the base of the pyramid. Now, how do we do that? If I know this, which is h, and I know this, which is 10 root 2 minus 5, how can I figure out this? Well, once again, you use similar triangles. And those similar triangles this time are this triangle and this big triangle. Because of the slant of the diagram, I know it doesn't look perfect, but trust me, those are similar. So that means that this over this is the same as this over this, that relationship. So if I label this big H, that means that big H over this, which is D over 2. Remember, this represents half of the diagonal of the square. That is equivalent to this over that, which is my small h over 10 root 2 minus 5. Now h is what we're interested in. Now d over 2 we calculated earlier, it's just 10 root 2. H we have as 14.26, and then we've got this 10 root 2 minus 5. And now it's just basic mathematics, crunching out some numbers with your calculator. And h is equal to this 14.26. And that 10 root 2 minus 5 is equivalent to approximately 9.142. And if you cross multiply this 10 root 2, that is 14.14 approximately. And if you calculate that, it comes out to approximately 22.05. And of the answer choices, the one that 22.05 is closest to is choice B, 22.1. So number 24, the answer is B. There are many positive integers n with the following properties. The digits of n include at least one of each of the digits 3, 4, 5, and 6. The digits of n include no digits other than 3, 4, 5, and 6. And the sum of the digits of n is 900, and the sum of the digits of 2n is 900. When the largest and smallest possible values of n are multiplied together, the number of digits in the resulting product is. Well, let's first make a little table here. We have n, 2n, and we have the sum of those digits. Well, when n is, say, including the number 3, 2n will be 6. And the sum of those digits obviously are 6. When it's 4, 2n would become 8, and the sum is 8. But when you have 5, you multiply it by 2, it becomes 10. The sum of the digits of 10 are 0 plus 1, which is 1. And then if you have a 6 and you multiply it by 2, it becomes 12, and the sum of the digits of 12, 1 plus 2 is 3. So that small table gives me the following conclusion, that if I just have n and I have a certain number of them, say I have w 3s, I have x number of 4s, y number of 5s, and z 6s, the sum is calculated as 3w plus 4x plus 5y plus 6z. And they tell me in the question that sum has to be 900, the sum of the digits. Now let's look at 2n. This was for n. For 2n, in a very similar way, if I have w6s and x8s and y, resulting in 10 because I have 5 y's, and then I had z6s that result in 12s, the sum is calculated as follows. It would be 6w plus 8x plus 1y plus 3z. See, I have w3s, but when you multiply it by 2, it becomes a 6. And that's why I have to use w times 6, because 6 is the sum of that number. The sum of the digit of 6 is just 6. If I have x 4's, when I multiply it by 2, it becomes 8. So now it becomes 8 times x. Y 5's, well, when I multiply by 2, it becomes 10. The sum of the digits of 10 is 1. That's why it's y times 1. And finally, if I have z 6's, when I multiply by 2, I get 12. The sum of the digits of 12 is 3. That's why the sum of the digits of 2n is 3 times z. And that's what I have here. And that is also 900 according to the question. So these are my two equations that I originally are able to make just with the information in the question alone. So now let's call these something. Let's call this, say, equation 1 and equation 2. And then let's start manipulating these. So say 2 times equation 1 minus equation 2, I think will help me out. I get, let's see here, 6w plus 8x plus 10y plus 12z. And if I subtract, I get minus 6w minus 8x minus y minus 3z. And on the other side, it would be 1800 minus 900. So the good news is the w's and x's go, and all I'm left with is 9y plus 9z is equal to 900. Divide through by 9, and I get y plus z is equal to 100. So this is a very important finding. If y plus z is equal to 100, then that means I can substitute that back into this original equation to simplify it a little bit. That becomes 3w plus 4x plus 5y plus, I'm going to break up that 6z into 5z plus z, and that's 900. So this becomes 3w plus 4x plus 5y plus z is 900, and then y plus z is 100, so I can substitute that in and just get 3w plus 4x plus z, and then bring the 500 over to the other side. So this is my second equation. Now, at this point in the question, we have to start talking about what it is they want us to maximize and minimize. They want us to find two values of n. The first is n max, and the second is n min. The maximum value of n and the minimum value of n. Now, for each of these, the sum of the digits will be basically x plus w plus x plus y plus z, like this. So if the number has w 3's and x 4's and y 5's and z 6's, the sum of those digits is x plus y plus z, w plus x plus y plus z. And therefore this one has to be first maximized, and we also have to find the minimum. The minimum possible value and the maximum possible value. Now y plus z we already got as fixed as 100 right here. So that means this really just boils down to finding that. So since y plus z is fixed as 100, we really just need to be worried about w plus x. We have to first maximize w plus x and then minimize w plus x. So it makes it a little bit easier for us. So that's what we're going to concentrate on, trying to find the maximum value of w plus x and then the minimum value. So first let's concentrate on figuring out the maximum, and then we'll figure out the minimum value. So let's use this equation, since that's one of the only equations we have. We've got 3w plus 4x plus z is equal to 400. I'm going to factor this 3 times w plus x, and then put the z and that 1x over to the other side. Now, we want to maximize w plus x, right? This is what I have to do here. So if I want to maximize w plus x, that means I've got to minimize z and x. So to maximize w plus x, I have to minimize z and x. Well, if you recall, there has to be at least one value of each of those numbers. So x has to be at least 1, and z has to be at least 1. X was representing the number of 4s, and z was representing the number of 6s, if I recall. So what's the minimum? Well, I can choose 1, but if I choose 1, what will happen for z and x is I won't get a number that is divisible by 3. See, watch what happens. I get 400 minus 1 minus 1, and it's got to be divisible by 3, and unfortunately it's not. Okay, no problem. Instead of 1 and 1, how about if I choose 2 and 2 for my values of x and y? If I do that, then I get 396, and 396 is indeed divisible by 3. Because remember, all of these have to be integers. They represent the number of digits. So w plus x, therefore, if I divide through by 3, is 132. So the maximum value of w plus x plus y plus z is 132 plus y plus z, which is 100. So that's 232. So I just got my maximum value. That's the maximum number of digits in a number n, where the sum of the digits is equal to 900. And the sum of the digits of 2n is also 900. Now we get to the next one, which is minimum. So in the same way, I have to take this and minimize my value for w plus x. So same scenario, but now I'm looking for a minimum. So what I'm going to do this time is factor again. I'll get w plus x, but I did a little bit of fancy algebra there, so I have to add w to this side. That's the only way I could have gotten this. In this equation, if I want to minimize w plus x, I have to maximize my z, and I have to minimize my w. Now let's look at the parameters. W is got to be greater than or equal to 1. Z also is greater than or equal to 1. But if you recall, y plus z was equal to 100. So that means z has an upper limit of at least 99. Because y has to be at least 1. So y being at least 1 leaves that z has to be at least 1 less, so it can be maximized as 99. So let's do that now. Let's maximize z and minimize w with these parameters. And when you do, you get the following values. Z, we can use 99. But the minimum w, if I try 1 or 2, this will not become something divisible by 4. So the first time it works is when you use w equals to 3. And when you do, you get 4 times w plus x is equal to 400 minus z, which is 99, plus w, which is 3. And this becomes 301 plus 3, which is 304. And therefore, w plus x is 304 divided by 4, which is 76. So the minimum value of w plus x is 76. So therefore, w plus x plus y plus z, that will be 76 plus 100, because y plus z was fixed as 100, and that's 176. So this is the minimum value for this number of digits for an n that has the properties in the original question. So now we have to take the n max and then multiply it by the n min and figure out how many digits are there. Well, the number of digits in n max is 232. The number of digits in n min is 176. We calculated that here and that here. Well, when you multiply two numbers together, you take the number of digits in the first and the number of digits in the second and add them to figure out the number of digits in the product. So that's how you figure out the number of digits in the product. And 232 plus 176 is 408. And that is the answer to the question. So, number between 0 and 100, does the equation have exactly two pairs of positive integers mn that are solutions? We have an equation, and I'm going to make a few substitutions to make this a bit digestible. The first substitution is 2 to the power of m squared will be a, 2 to the power of n squared will be b. Now, we know that k is odd, so that means k is of the form 2x plus 1. So that means that k minus 1 over 2 is x, and therefore k minus 1 is equal to 2x. That's perfectly valid. And therefore, another type of term that I will need to figure out this whole expression involves k's, but let's just simplify this first, and then we'll make these substitutions. So we've got 2 to the power of m squared, all to the power of 4, right? I'm breaking it up. 2m squared over 2n squared times 2 to the power of 4. And on this side, we've got 2 to the power of k times 2 to the power of 4 plus 2 to the power of m squared to the power of 3 times 2 to the power of n squared times 2 to the power of k. All right, so now let's make our substitutions. This is going to be a to the power of 4 plus a times 2 to the power of 4, which is 16. So 16a over b, because this is b, right? Making my substitutions now. And then on this side equals 2 to the power of k times 2 to the power of 4. Well, that's just 16 times 2 to the power of k, like that. And then this one will be, we've got a to the power of 3 times b times 2 to the power of k. Okay, so far there's no tricks, just standard substitutions. Okay. And also, interestingly, I thought that we might need to use this substitutions, but we haven't. Okay, no problem. Now let's start to simplify. Let's get a common denominator here. So this is going to become a to the power of 4b plus 16a over b. And on this side here, I can factor out a 2 to the power of k, and when I do, I get 16 plus a to the power of 3b. And let's see here. I guess we can put this in the denominator over here. And when we do, we get a to the power of 4b plus 16a, and that will become 16b plus a to the power of 3b squared, and that's just equal to 2 to the power of k. Okay, great. So far, it looks pretty good. And factor out an a from the top, and that gives me a to the power of 3b plus 16. Factor out a b from the bottom, and I get 16 plus a to the power of 3b. And look at that. This is the same as this. 16 plus a to the power of 3 times b, 6a to the power of 3b plus 16. Okay, great. So all we're left with is just a over b is 2 to the power of k. So it turns out to have a very nice, simple result at the end. And that's very, very helpful. Now let's see what we can do with that. So at this point, we can go back and make our substitutions to further understand this. So a over b is equal to 2 to the power of k, and k is odd. Well, what's a? Well, we had called it 2m squared, and b was 2 to the n squared. That's 2 to the k. Well, that basically just means 2m squared minus n squared is equal to 2 to the k. Since the bases are the same, the exponents must be the same. So that means m squared minus n squared is equal to k. Wow, we are pretty much taking a monster right here and simplified it all the way down to just this right here. M squared minus n squared is equal to k. Now we can work with this. And another good thing about this question is there's no trick so far. No algebraic tricks that needed to be used, just standard mathematics. Now at this point we have to start thinking, okay, it's great that we have it in this form, very helpful, but where do I proceed from here? And first of all, what is the question asking me? So let's backtrack and understand what is it that they want in this question. They want you to first understand that k has to be odd. So that's the first condition. Also, k is between 0 and 100. So those are the parameters. And then they want you to figure out which of these values of k, if you substitute it obviously into our very simplified equation, would give you two solutions for m and n. So the best way to explain that is with an example. So, for example, let's say k is equal to 15. First of all, let's see, does it satisfy my two rules? Is it odd? K equals 15 is indeed odd. And is it between 0 and 15? Well, of course it is. Now, we take our beautiful equation, substitute k equals 15. Well, that, as I'm sure you know, factors into m plus n, m minus n, like that. And now we've got a choice, right? Either this can be 15 and this can be 1, or this could be 5 and this could be 3. That's how you'd get two numbers to multiply to equal 15. Let's try both. M plus n is 15. M minus n is equal to 1. If I add these two, I get 2m is equal to 16. M is equal to 8. And therefore n, if I substitute that back into here, m would be 7. All right, great. So I got one solution for mn, 8, 7. Let's see. That was using these numbers. Now let's see what happens with those numbers. All right. With those numbers, m plus n would be 5. M minus n would be 3. Adding those, you get 2m is equal to 8. M therefore would be 4. So m equals 4 back into any of those original equations, it will give you n equals 1. So there we go. We got another one. mn is 4, 1. So for k equals 15, we got two solutions for mn. And that's exactly what they want you to figure out. For how many odd integers k between 0 and 100 does this equation, which we simplified greatly, have exactly two pairs of positive integers mn that are solutions? So it basically boils down to exactly what I did for k equals 15 for this very nice equation. Now you say, well, okay, that's great. I understand that completely. But here's the thing. There's a lot of numbers between 0 and 100 that are odd. There's 1, there's 3, there's 5, 7, right? All the odd numbers from 0 to 100, there's 50, I would imagine, right? There's no way I'm going to go through that for 50 numbers. You did it for 1, k equals 15. Do I really have to do that for 50 numbers on a math contest? There's no way. And the good news is you don't have to do it the long way. There's a shortcut, and here is the shortcut. What I did here is something that needs to be done for every single scenario that works. And what I basically did was I broke up k into its factorization, right? Either 1 times 15 or 3 times 5. And there was two of them. Here's 1, here's 2. Each of them gave me a solution. So that's the general rule, that we need to break up k into two factorizations. Each one will produce one solution for mn. And that is the general rule. So I have to see, how do I do that for values of k? And we are going to have three scenarios, three cases. Case number 1 is basically when k is of the form p times q, where p and q are prime numbers. And that will help us tremendously. And one example of that is actually what I just did, 15. If you notice, k in this case would have been equal to 3 times 5. And what that does is allow you to come up with two factorizations. The first one is just 1 times the number, so 1 times PQ, which I had done here, 1 times 15. The second factorization would be P times Q, like that, which is this one, 3 times 5. And each of these will produce 1 mn. So this will give me 2 solutions. All right, now I got to figure out what values of k satisfied this scenario. All right, well, the good news is that we don't have that big of a range. And since p and q must be prime, we can sort of skip over a lot of numbers. So I don't really want to bore you to death and talk you through it, but 3 times 5, 15, that's one of them. 3 times 7, that's another one. 3 times 11, right? You just have to come up with combinations where both p and q are prime and that the final number is between 0 and 100. And there's only a finite number. 3 times 13, I'm doing all the 3's now. 3 times 17, and you notice I'm only using prime numbers. 3 times 19, 3 times 23, 3 times 29, and 3 times 31. At that point, we start getting numbers that are greater than 100, and we don't want that because our range is between 0 and 100. All right, so this was what, 15, 21, 33, 39, 51, 57. These are values of k, by the way. 69, 87, and 93. Okay? Now I've exhausted the 3's. Now let's see multiples of 5. 5 times 7, 5 times 11, 5 times 13, 5 times 17, and 5 times 19. And I think after that we'll get over 100. So this is what, 35, 55, 65, 85, and 95. Okay, let's see how many more we can get. How about 7's now? I've exhausted the 5's. My next prime number is 7. 7 times 11, 7 times 13, and I think that's it to stay within my range. Okay, these are the only ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I got 16 values of k for which this will work. Okay, put that here. Now let's see, is 16 one of the answers? 16 is not one of the answers, and that's probably a good thing, because otherwise you'd probably circle it and move on, because that basically means there's a few more. Okay, scenario number 2. This scenario was with k equal to pq. Now things get a little bit more complicated. K could be of the form p to the power of 3. If it is, our two prime factors, or our two factorizations, a better way of explaining it, will be 1 times p to the power of 3, or p times p squared. Okay? Now we got to figure out which values of k satisfy that. Well, p can only be 3, because if you use 5, it would be 125, and that would become outside of our range. So p equal to 3 is the only one. So 27, that's my only value of k that will satisfy this condition. All right, well, that 27 gives me one more. And there's only one other scenario. That is when k is equal to p to the power of 4. That will give me factorizations as follows: either 1 times p to the power of 4, or p squared times p squared. That would be another factorization. And the only value that will work for p to the 4, again, is 3 for the value of p. That will be obviously 81, because if you put any other prime number, it becomes outside of that range for k. And that gives me one more value, namely 81. And there we go. we've got 16 here, we got 1 here and 1 here. The total will be 16 plus 1 plus 1, which is 18. 18 is the answer to this very challenging question. And that means for number 25, the answer is D. Points P, R, S, and Q, T, U are on the parabola with the equation y is equal to x squared minus 1/5 mx plus 1/5 n, so that PQ equals 13 and the slope PQ is 12 over 5. For how many points Mn of positive integers with n less than or equal to 1,000 is R plus S plus T plus U equal to 27? Let's just draw a very brief diagram, and perhaps this parabola looks something like this, and we've got to choose 2 points here, P and Q. And when we draw a line from them, they're going to say that that slope is 12 over 5. So this is just to illustrate what that looks like. And therefore, we can now calculate using the points. P is RS and Q is TU. So using those 2 points, since the slope is equal to 12 over 5, we can use those 2 points to get a little equation. So U minus S over T minus R will be equal to 12 over 5. And I have no idea what is U and S and T and R, but I know the ratio. So that means U minus S must equal some multiple of 12, and T minus R is probably some multiple of 5, and that's how you get a ratio of 12 over 5. Okay? All right, so that's the first little piece of mathematics. Now the next thing is this piece of information right here, that the distance between P and Q is 13. So using the distance formula and those 2 points, we can find the following equation, that U minus S squared plus T minus R squared is equal to 13 squared, right? So I'm going to substitute these points in to figure out what K could possibly be. U minus S is 12K, square that. T minus R is 5K, square that. And I've got 169 here. So this becomes 144K squared plus 25K squared, and that is equal to 169. So this is now 169K squared is equal to 169. So that means obviously K is equal to 1. All right, great. So putting that back into these two guys, that gives me that U minus S is equal to 12, which would be giving me U is equal to 12 plus S. And then it gives me that T minus R is equal to 5, which would give me that T is equal to 5 plus R. So my 2 points now, I have P, R, S, and I have Q, T, U. But what I can do is I can put Q in terms of R and S, since I have these 2 relationships right here. That will allow me to put T as 5 plus R and U as 12 plus S. So there we go. That at least helps me a little bit. I can get rid of some of the variables, and now I can work with less variables, which is always better than more variables. Okay, so here we go. Now let's turn our attention to this part of the question. They want us to figure out a situation where R plus S plus T plus U is equal to 27. All right, but I know some really nice relationships here, so let's substitute those in. That T is equal to 5 plus R and U is equal to 12 plus S. So I've got R plus S plus T, which is 5 plus R, plus U, which is 12 plus S, is equal to 27. So this simplifies to 2S plus 2R is equal to 10, and therefore S plus R is equal to 5. So that's my first piece of information that is very helpful. Now both those points P and Q are on the parabola, so we can substitute those points into those parabola. So substituting, we get the following. We get the first equation, which would be substituting this point, and that would basically give me s is equal to r squared minus mr over 5 plus n over 5. And then substituting that one, we get a little bit more algebra there. We get s plus 12 is equal to 5 plus r squared minus m times 5 plus r all over 5 plus n over 5. And then when you expand this, you get s plus 12 is equal to r squared plus 10r plus 25 minus m minus mr over 5 plus n over 5. And then what we do now is we will subtract from 2 equation 1 and simplify. And when you collect like terms, you will get just 12 is equal to 10r plus 25 minus m. Simplifying and isolating for r, you get m minus 13 over 10 is equal to r. So this is my next helpful piece of information. Now I will take this very helpful piece of information and I will substitute it back into 1. Equation 1, that is, right here. And when I do and I put that in, I get m minus 13 over 10 all squared minus m times r, which is m minus 13 over 10. And then, of course, don't forget the 5 there. And then plus n over 5. Once you simplify this big, long thing, you get the following. You get s is equal to 1 over 100 times minus m squared plus 169 plus 20n. This is another very helpful equation. So, to summarize, we now have 3 very important equations that I have placed a star. We have s plus r is equal to 5. R, this guy, is equal to this. S here is equal to this. So I will put what I have for r there and what I got for s right there. So that's my next step. R plus s is equal to 5. So let's put r, which is m minus 13 over 10 there. S is over here. Let's put that over for the value for s. So it'll be 1 over 100 times minus m squared plus 169 plus 20n is equal to 5. Okay, so now we have to simplify this. And when you simplify, you get 20n is equal to m squared minus 10m plus 461. If you complete the square, you will be able to factor this very nicely. And you get 20n is equal to m minus 5 squared plus 436. All right. So now let's talk about this now. This is the equation that pretty much we're down to. This is our sort of final equation that we need to talk about and discuss and all that stuff. Well, 20n is obviously an even number. 436 is an even number. So that means this guy has to be even. And therefore, m minus 5 is even. And therefore, m is odd. Okay? So I hope that made sense. So since m is odd, I will let m equal to an odd form, which is 2k minus 1. Right? Any odd numbers of that form. And I will now substitute that back into this guy right here. All right? So substitute m is equal to 2k minus 1 back into my equation here. So when I do that, I get 20n is equal to 2k minus 1 minus 5 all squared plus 436. When you simplify and collect like terms, you get 20n is equal to 4k minus 3 squared plus 436. And I can divide through by 4, and that just gives me 5n is equal to k minus 3 squared plus 109. All right. Now recall that n in the question was given to us as being less than or equal to 1,000. So we can use that to help us out. And what I'm going to do is make a little table and try to figure out how can I make this equation here work. Well, we need to first consider values for k minus 3, then values for k minus 3 squared, and then of course the entire equation, which is k minus 3 squared plus 109. Now, k minus 3 squared plus 109 is equal to 5n. So that means that is a multiple of 5. And multiples of 5 end in either 5 or 0. All right? So what I'm going to do is I'm going to place only the units digit into those boxes to figure out what my k can be. Well, k minus 3, whatever it is, the units digit is anywhere from 0 to 9, right? Those are all the possible units digits. Okay, if that is the case, when I square it, what happens? Well, the units digits then become 0, 1, 4, 9, 6, 5, 6, 9, 4, and 1. Okay, what happens when I add a 109? Well, then the units digits become 9, 0, 3, 8, 5, 4, 5, 8, 3, and 0. Well, which one of these end in either a 0 or a 5? This one, this one, this one, and this one. So that means that k minus 3 has to have a units digit of either 1, 4, 6, or 9. All right. Okay, so since my n is less than or equal to 1,000, don't forget about that, a very important parameter. That means that k minus 3 squared plus 109 is less than or equal to 5,000, since it's equal to 5n. Correct? So that means that k minus 3 squared is less than or equal to 4891 when you subtract the 109. And when you take the square root, you get k minus 3 is less than or equal to 69.9. But remember, k is an integer. So k minus 3, I should say, has to be less than or equal to 69. K minus 3. Now we have to talk about what values of k can I plug in that will give me units digits of either 1, 4, 6, or 9. Correct? And keeping in mind that k minus 3 is less than or equal to 69. So I got 72, 69, 67, 63. If you notice, if these are k's, k minus 3 will equal numbers that give these as the units digit. Okay, that's what I'm doing. So continuing, I get 62, 59, 57, 53. You'll see that there's a pattern here. 52, 49, 47, 43, and so on, right? So I'll just fill them all in. And there you go. There's my entire list, where k minus 3 is less than 69. And I'm choosing values of k so that k minus 3 will have a units digit of either 1, 4, 6, or 9. And how many did I create in total? If you add all those up, it's 29. And each value of k from this list of 29 will give one value of m, because if you recall, m is equal to 2k minus 1. And then once you have a value of m, you plug it back into here to get a value of n. So each of these 29 values of k will give a value of m and a value of n. Therefore, that would give me 29 pairs of the form mn. And that is the answer to the question, 29. So that would mean that number 25, the answer is D. There are f fractions m over n with the properties m and n are positive integers with m less than m. M and n over n is in lowest terms. N is not divisible by the square of any integer larger than 1, and the shortest sequence of consecutive digits that repeats consecutively and indefinitely is in the decimal equivalent of m over n has length 6. We define g is equal to f plus p, where the integer f has p digits. What is the sum of the squares of the digits of g? Well, we start with a simple example to illustrate what we need to do. So let's say I have some number. I'll just make up a number. 0.58, 123, 123, 123, and so on, where the 123 is obviously repeating. Now I want to create a sort of a fractional form of this. So what I'm going to do is show you how to do that. And then we can extrapolate to other similar sort of numbers. First thing is multiply both sides to get this part into an integer. Well, in this case, I would have to multiply by 100 to bring it over 2 decimal points. So it would be 58.123 repeat. All right? And then what I can do is bring over just the integer part and then leave the decimal part on the other side. 1, 2, 3 repeat. Now I want to do this again, but I'd like to do it in a way so that I bring at least one repeat to the other side of the decimal. Well, in this case, it's only 3 digits that repeat, so I have to multiply by 1,000 in order to do that. So I've got to multiply by 1,000 on both sides to get part of it over to the other side of the decimal. So 1, 2, 3 times 1, 2, 3 repeat. Okay, so again, bring the decimal part separate from the integer part. So I do that by bringing over the 123 to the other side, and then on this side just leave that 0.123 like that. Okay, well, this 0.123 we already have in terms of n, so substitute it in. 100 n minus 58. So as you can see, I got rid of all the decimals, and I can write a nice formula without decimals to represent this big long decimal, which is n. Okay, so far this is how far we've gotten. And then now let's put the 123 on the other side and put this on that side. So 1000 times 100 n minus 58 and minus 100 n minus 58. Okay, let's factor out that 100 n minus 58 since it appears twice. And when you do, you get 1000 minus 1. Okay, we are almost ready to isolate for n. And it looks like 123 over 999, correct? And then that's going to be 100n minus 58. And then 123 over 999 plus 58 will be 100n. And then finally we'd have to divide through by 100. But before I do, let me just multiply top and bottom here by 999 to make sure we get the same denominator. And then now I can divide through by 1 over 100. 123 plus 58 times 999 over 999. Okay, so that big long process was to show that any such decimal with repeating digits can be converted into a fraction in a very similar way. So you can sort of do the same kind of story with any such decimal expression. But we have to get sort of a general term. This isn't great. This was only for this specific. It's meaningless, really. But it gives you a little bit of a pattern, and that's what we are looking for. So let's talk about it. We have n. We've got this thing, which don't really need to concentrate on too much, so I'll just call it k. But what's on the bottom is important. It's 100, which I'm going to write as 10 to the power of 2. And we've got 999. Okay, so this is where we have to recognize what is happening. The 2 right here comes from the fact that there was 2 digits there. Okay, correct? 5, 8, 2 digits, that's why there's a 2 there. Because remember, initially I had to multiply by 10 to the power of 2 in order to get that 5, 8 to go on the other side of the decimal. The 9s correspond to the fact that there's 3 of those digits that repeat. The digits that repeat were 1, 2, 3, right? 1, 2, 3 repeats itself. And there's 3 of those digits, that's why there's 3 9s. So, what I can do is I can sort of make a little bit of a general formula as follows. N is going to equal some integer. The numerator actually is not really that important. But what is important is 10 to the power of p times 9 dot 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 9, where the number of 9s is q. And the p represents how many digits I have here, and the q represents how many digits I have there. Okay, so I hope that makes sense. I know it's a little difficult, but so far, hopefully it's not too bad. Okay, so we are not interested in this specifically. That was just an example. We are interested in m over n. And m over n is going to be of some form. We have no idea, but it's some form, like we're going to have, obviously, a 0 followed by some whole bunch of A1, A2, some digits all the way up until, say, AP. And then what's going to happen is we are going to have 6 repeating digits. B1, B2, B3, B4, B5, B6. Remember, it's got to be at least 6, so I'm going to start with 6. Now let's look at what that formula will look like. Well, the k, remember, the numerator is not that important, but the 10 to the power of p, because there's p of them. Remember, there's p digits there, so that's going to be 10 to the power of p. And then this part, you put 9's But how many 9s? Q 9s. And in this case, my Q is 6. So it's going to be 999, 999. Okay? So that is the first step of the question. Now let's cross multiply, and when we do, we get nk is equal to m times 10 to the power of p times 999, 999. Now, since m over n was in lowest terms, that means n must be a divisor of this. So let's first list what are the prime factors of that big long number. Well, first we'll break it up into 2 to the power of p times 5 to the power of p. And then the 999, 999, that is 3 to the power of 3 times 7 times 11 times 13 times 37. So that means n contains those prime factors. And therefore, we can conclude that n must be a divisor of those prime factors multiplied together. And when you do multiply them all together, you get 1, 1, 1, 1, 1, 1, 0. So this is a very important number. All right. So that means m over n is of the form some numerator, we'll call it s, over that very important number. And now let's revisit our criteria. The first criteria is that m has to be less than n. Okay, so that means s has to be less than or equal to 1, 1, 1, 1, 1, 0, 9. Because it's got to be less than n. And it's got to be positive, so obviously greater than or equal to 1. The next criteria is that m over n has to be in lowest terms. Okay, I think we can do that for any such m over n. We can always lower it, so can be done, whatever it is. The next criteria is that n is not divisible by any square. And that is true because we don't have any perfect square in the prime factors. We have individual prime factors. So if you look at the prime factors, you will see that that's not going to be an issue. Because if we had, like, for example, something like 7 squared, then yeah, but we have just individual prime factors that make up this number. And then now we have to look at the fourth criteria, which is the toughest one, which is that m over n is of the form that it repeats, and it repeats 6 times, at least 6 times. So it's basically of the form 0 and then a whole bunch of a's, ... until some AP. These are not repeating, but then we've got at least B1, B2, B3, B4, B5, and B6 that repeat. So now we have to concentrate on this guy right here, this one. So we have to get this s over 1, 1, 1, 1, 1, 1, 0 into some form that shows that it will look like this. Okay, well, this is where some fancy algebra comes in. We can factor out a 1 over 10 and put a 9 up there, and then here we'll get 999, 999. I just manipulated this number a little bit. Nothing has changed. Now this can be written, we can factor out the 1 over 10, and we can break it up into an integer and a fraction. So if this is divided by this, there would be some integer and then a fraction that's left over. So I'll let y represent the integer, and the fraction I'll represent as some numerator over 999, 999. And then again, the integer we're not so worried about, but the numerator, which I denoted as z, that one is obviously going to be something less than this 6-digit number. Now, it could be less than 6 digits, but it has to be at most 6 digits. So I'll call it a 6-digit number, R1, R2, R3, R4, R5, R6, like that. And the denominator is that 999,999. Well, when you multiply through, after you adding it, it will look as follows. First, when you add this, it becomes y dot R1, R2, R3, R4, R5, R6, all repeat, because that's what happens when you divide by that number. And then finally, when you divide through by 10, it will bring the y over one space to the other side. And then we have R1, R2, R3, R4, R5, R6, all repeating. So I showed how this can indeed look like that format. So far, so good. So now we have to figure out how many of these fractions can we make. Well, we noticed that the numerator can be anywhere from 1 to 109, and every one of those numerators will create one separate fraction. So that's how many we will get. But here's the thing. We will also sometimes get shorter sequences because we have to have sequences that are at least 6 in terms of the repeating part of it. So we have to look at how many shorter sequences we have and then remove those from that grand number. So the grand number was 1111109, right? Because that's how many values of s we can get. Well, the number can be written as follows. We can have s over 2 times 3 times 5, and that will be s over 30. So the number of values of s will be, in this case, 29. Right? 1 through 29, basically, when you have a fraction like this. This will give you a repeating decimal that has a shorter sequence than 6. And these, of course, came from the prime factors that we originally had up here. Let's see, what other ways can I get shorter sequences? If the fraction is of the form s over, and this is of course m over n, 2 times 3 times 5 times 11. That will also give shorter sequences. Repeating sequences perhaps, but definitely shorter than 6 digits that repeat. And this is s over 330, and the number of values of s here will be from 1 to 329, so that's 329. And there's one more that will give shorter sequences, and that is s over 2 times 3 times 5 times 37, and that is s over 1110, and the number of values of s there obviously will be 1109. And there's no other forms of s that we need to consider. So, what is the total number of values of s? Well, it's not as simple as just adding them. There's an overlap here. And after you study the overlap, you will find that the total of these is actually 1. You get 1109 plus the 329, but you have to minus that 29 to account for an overlap that exists. And that will give you the number of sequences that you have to subtract from the grand total. So to get our f, which is the actual number of fractions m over n, it would be the grand total, which is 11109, minus these guys. So 1109 plus 329 minus 29. And when you do that math, you get 1109700. Now, p is the number of digits that are in f. And as you can see, this has 7 digits. And g is equal to f plus p. So that would be 1109700 plus 7, which is, of course, 1109707. And now, finally, we have to calculate the sum of the squares of g. In particular, the sum of the squares of the digits. So here's g. Sum of the squares of the digits would be 1 squared plus 1 squared plus 9 squared plus 7 squared plus 7 squared, which is, of course, 1 plus 1 plus 81 plus 49 plus 49. And that is equal to 181. And therefore, the answer to this most challenging question and time-consuming question is 181, which is choice E. The set A 1, 2 until 2045 contains 2045 elements. A subset S of A is called triple free if no element of S equals 3 times another element of X. For example, 1, 2, 4, 5, 10, 2, 0, 4, 3 is triple free, but 1, 2, 4, 5, 10, 6, 8, 1, 2, 0, 4, 3 is not triple free. The triple free subsets of A that contain the largest number of elements contain exactly 1, 5, 3, 5 elements. They are n triple free subsets of A that contain exactly 1, 5, 3, 5 elements. The integer n can be written in the form p to the power of a, q to the power of b, where p and q are distinct prime numbers and a and b are positive integers. If n capital is equal to p squared plus q squared plus a squared plus b squared, then the last 3 digits of capital N are. This question can be simplified, and we will do it in that simple way. The first thing, of course, is to understand that once you find the value of n, the rest is a piece of cake, because then you just have to deal with this algebra, and that's very easy. So we will concentrate really on just the first part of the question, concentrating on trying to find the value of this n. So first, let's start off with a small subset. That's a very big one, from 1 to 2045. It would take forever to explain and would become very confusing very quickly. So let's start off with a simple one with only 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, my k is 9, k representing the number of terms. Now my goal is to find triple free subsets. So triple free subsets from the definition are basically a subset where no element is 3 times another. So for example, I can't put 3 and 9 in a subset because 9 is 3 times 3. So I've got to make subsets that are triple free. The strategy is as follows, and once you understand the strategy, the question becomes a lot easier. Here we go. What you do is you break up this into different groups. The first group starting with 1 and triples. So 1 times 3, 3 times 3, like that. That's the first group. Then you go to the next number, 2, and do the same thing. 2 times 3 is 6. 6 times 3 is 18, but I don't need to worry about 18 because I'm only going up to 9. All right, let's keep going. Next one would be 3. Well, 3 is already included. Next one would be 4. 4 times 3 is 12. Well, that means 4 just appears by itself. 5 appears by itself, so does 6, and so does 7. Well, 6 actually I already have here, so don't include 6. So as you can see, you got to make sure you don't include things that have already been included. So these are my subsets. Now, to make a triple free, I have to choose one or more from each of these groups. I have to choose the max, because the key here is right here. The largest number of elements, that is the key. I have to make the subsets have the maximum amount. So I have to choose the maximum from each subset. From here, I can only choose one. I can only choose one number. Here, I can only choose one number. Here, I can only choose one number. But from here, I've got two choices, either the 2 or the 6. I got two choices. From here, it's not tricky, but you just have to do a little bit of thinking. What can I choose from here? Remember, I've got to choose it in a way so that I make the maximum. Well, I can't choose 3 and 9 because 9 is 3 times 3. I can't choose 3 and 1. Those two can't be together. But I can choose 1 and 9. And there's only one way of doing that. Now you say, well, what about 1, 3, and 9? I can't do that because 9 is 3 times 3. And you say, well, what about just 3 by itself? No, because that would not make it the largest. I have to make it the largest. I'm forced to make the largest subset. I have to choose the most numbers from each of those subsets. So then what you do is you multiply these guys. These guys right here. And that gives you the total. So in this case, it's just 2. So what that means is that when k equals 9, I have 2 triple free subsets. And since there's only 2, we can just list them. We can easily list them 1, 9, 2, 4, 5, 7, 8, and 1, 9, 6, 4, 5, 7, 8. I didn't write them in chronological order. I'm just going by these subsets. Okay? So hopefully, with a very small example, you're kind of getting how this works. Now let's move up, not to the big one. Let's move up to a slightly bigger example. K equals 27. Now, I've got 1, 2, 3, and so on, right? All the way up until 26, 27. That's my big set. And then I've got to do the subsets, just like how I did here. Okay, starting with 1. 1, 3, 9, 27. Then let's go to 2. 2, 6, 18. Remember, I got to create these sets. 3 is already included. 4, multiply by 3, 12, and then that's it. Can't go to 36 because my list only goes up to 27. 5, and 15, right? 5 times 3 is 15. 6 is already there. 7, yeah, that will be good. 7 times 3 is 21. 8, yes, 8 times 3 is 24. 9's already there. 10 times 3 is 30, but 30 goes beyond, so 10's going to appear by itself. And so will 11, so will 13. Skip over 12 because that's already there. So will 14, so will 16, 17, 19, 20, 22, 23, 24, and 26. Make sure I skip over ones that have already been included. Now, as we did before, let's figure out how many do we get. Well, from each of these individuals, you can only choose one, right? So 1, 1, 1, there's only one to choose from each of those subsets since there's only one number in the subset. But with these guys, there's 2. There's 2, 2, 2, and so on. Now we get to this guy, and as before, we can only choose 2 and 18. And I think I had explained that sort of in the same way there. When there's 3 elements, you can only choose it in one way. And that is you have to choose the 2 on the opposite ends. You can't choose, obviously, 8 and 16 because 18 is 3 times 6. You can't choose the 6 and 2 because 6 is 3 times 2. And you can't choose the 6 by itself, even though it's valid, because we want to make the maximum amount of terms in that subset. as I had previously explained. Now we come to this guy. This is new. Okay, well, how do I select this? Okay, well, I can select the 1 and the 9. That's valid. I can select the 3 and the 27. And I can select the 1 and the 27. All of these 3 are fine. So there's 3 ways to select from there. I can't select 1 by itself because, as previously explained, I've got to choose the maximum number of elements. I can't select 3. There's no combination of 3 that I could select because they would break the rule that one element is 3 times the other. And I obviously can't select 4. So now I got to multiply this by this, by this, by this, by this. The good news is the 1s don't contribute to the product, so the 1s can be ignored. So that means I've got 3 times 2 to the power of 4, and that is 48. So that means there's 48 triple free subsets when k is equal to 27. And also, I hope you can notice that this number is in that form that they gave right here, p to the a, q to the b. So, q to the b. So, to calculate n, you just have to figure out p squared plus q squared plus a squared plus b squared, and that's very easy to do. Okay, so now that we've done 2 examples, one with k equals 9, one with k equals 27, I think we are ready to tackle the big guy. So here we go. So now we're going for the big one, all the way to 2045. So remember, 1, 2, 3, all the way until 2045. We have to now create the system. And in this case, k is equal to 2045. So here we go. Just like before. Start with 1, and then we have 3, 9, 27, 81, 243, and 729. And then anything above that, it would exceed the 2045. Now, here I'm going to write how many elements there are. And in this case, 1, 2, 3, 4, 5, 6, 7. So 7 will go here. And then here, I'll write how many, the number of such subsets. Well, I have to fill out the list first before I figure out how many there are. Let's try with 2. 2, 6, 18, 54, 162, 486, and 1458. Okay, that's another 7. And then let's go to the next one. Skip over 3 because 3's are already included. The general rule would be that nothing in the first column would ever be a multiple of 3 because those will already have been included. So just keep that in mind. That's actually a pretty important rule. Okay, with 4, 12, 36, 108, 324, and 972. Okay, well, this is 1, 2, 3, 4, 5, 6. Oh, okay. So that means we are now down to 6. So that means the ones that have 7 elements, there's only 2 of them. All right, so that is how we're going to do this. Now, I know it may seem like extremely time-consuming, but the good news is that it gets quicker. And you have to do a little bit of number crunching. So you make these lists as follows. So these ones you can continue. I'll just write them out. And as you continue to make this list, you find out quickly that you only have 4 that have 6 elements in it. The next ones have 5 elements. And then you just continue to make this list, dot, 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 like that. And then you'll get to 25, 75, 225, 675, and then 2025. This will be the last one of 5 elements. And you can count these up. There's not that many. There's only 11. Now you say, well, I actually see that there's more than 11. I see 16. How did you get 11? Well, here's a little bit of a trick you can use to get that 11. What you do is you take this number, 25, subtract from it 1 below that, so that's 9, and that gives you 16. Yes, there's 16 numbers, but we cannot include multiples of 3. So how many multiples of 3 are there among 16 numbers? Well, it would be 16 divided by 3. And just like the previous question, you have to take only the integer value. So it would be 16 minus 16 divided by 3 bracket, and that's 16 minus 5, which is 11. So as previously, I got 11. And that's a quick way of doing it. And then you just keep doing this. You just keep going like this all the way through. So same thing. So now we've done the 7 element sets, the 6 element sets, the 5 element sets. Now probably we're going to get down to 4 element sets. 26, 78, 234, and 702. And that is indeed 4 elements. And then you ... keep going until you get to the last one, that's 474. And that is going to be a 4 element set. And how many are there? Well, this is where you use your fancy trick. 74 minus 25. All right, so that is 49. And then 49 minus 49 divided by 3, the integer value. And that will give me 49 minus 16, which is 33. All right, great. Let's keep going. Now I'm at 76, because remember, 75 is a multiple of 3, and it's already here, so I can't include it again. So a little bit of thinking involved here. Not an easy question, but completely realistic. Okay, this is a 3 element set. And similarly, ... you keep going until you don't get any more 3 element sets. And 227 is the last one that gives you 3 elements. And now we have to figure out how many of them were 3 elements. Okay, 227 minus 76. 75, not 76. Remember, it's got to be 1 less. Okay, and that is 152. And then you do 152 minus 152 divided by 3, the integer value. And that is going to be 152 minus 50, so 102. All right, let's keep going. 228, I believe, is right here, so can't use it again. It's a multiple of 3. So we got to start with 229 and 687. So now we're down to 2. And then the biggest one is 680, 2040. And then that's it. All right. So again, 680 minus 228. And that is 452. And then, of course, 452 minus 452 divided by 3, the integer value. And that gives me 452 minus 150, so 302. All right, now we have to figure out one final column of a table. And that is, for each of these, what is the maximum? So I guess what I'm really talking about is choices. How many choices? What are the choices? So I'll start off with this end of the table. I think it's a little bit easier to explain. So when you only have 2 elements, you can either choose this guy or this guy. So for each of those, you got 2 choices. So I'll just put 2 right here. Okay. When there's 3 elements, if you remember, there's only 1 choice. And for example, you can only choose 227 and 2043. That's it, as previously explained. When there's 4, I think I had done that one too. You can have 3 choices. For example, if this was the subset, your 3 choices would be, or let's go with this one. It doesn't really matter. You can use either 26, 234. You could use 78, 702. or you could use 26 and 702. So these three choices are why I put a 3 there. Okay, now we get into the new territory, which is this guy. 4 elements we did, now we have to do 5 elements. Well, when there's 5 elements, interestingly, there's only one way of choosing. For example, if we have, say, this guy, we can only choose 10, 90, and 810. That's the only way of doing it. To choose the maximum and to choose in a way that the rules are satisfied, that no element is 3 times the other. All right, moving right along. If there's 6, well, there's going to be a little bit more complicated. So let's explain with that one. If there's 6 elements, there are 4 ways of choosing. So for example, you can use 4, 36, 324. You can use 12, 108, 972. You can use 36, and 972, or you can use 4, 1081, and 972. And as you can see, there are 4 of them. That's why I put a 4 there. So I hope this is making sense. And one last one has some good news, that there's only one way of doing it. So for example, if this was the subset, you can only choose 1, 9, 81, and 729. That's it. That's the only way to do it. So that's why there's 1 there. Okay, we are in the final step. We are basically at the point where you calculate n. And just like before, if you remember, with my examples where k is equal to 9 and k is equal to 27, that's the same way I'm going to do it up here for this one. N is going to be, I'll do it in red here, this to this power. So 2 to the power of 302. This to this power. But we don't really need to include that because 1 to the power of 102 is just 1. It's pointless to write that in. So I'll skip that. Then this to this power, that will actually contribute. This to the power of 11, don't need to put that in. 4 to the power of 4, that will definitely contribute. And then 1 to the power of 2, which is just 1. There we go. That's the value of n. And we can simplify this a little bit. Since this is 2 to the power of 2, this basically becomes 2 to the power of 310, 3 to the power of 33. And that is of the form p to the power of a, q to the power of b. And now our final step is to figure out big N, which was p squared plus q squared plus a squared plus b squared. Well, that's going to be 2 squared plus 3 squared plus 310 squared plus 33 squared. That number is 97202. We were asked to find the last 3 digits, 202. So the answer to this is 202, which is choice A, number 25. Let r be the square root of root 53 over 2 plus 3 over 2. There is a unique triple of positive integers ABC such that r to the power of 100 equals this. What is the value of a squared plus b squared plus c squared? Let's first concentrate on the value of r, which they have given as the square root of root 53 over 2 plus 3 over 2. Take the square root, the radical sign disappears, and then we can proceed. Multiply through by 2 to get rid of the fractions, and we get root 53 plus 3. Bring the 3 over. 2r squared minus 3 is root 53. And now let's square both sides again to get rid of that root 53. And when you do, you get 4r to the power of 4 minus 6r times 2, which would be 12r squared plus 9. And that equals 53. So put everything on one side and we get 4r to the power of 4 minus 12r squared minus 44 is equal to 0. And therefore, if you divide through by 4, you get r to the power of 4 minus 3r squared minus 11 is 0. And therefore, r to the power of 4 is equal to 3r squared plus 11. So this is a very important finding that's going to be used several times in this question. Okay, now let's concentrate on that equation, this big long equation that they've given us. So r to the power of 100 is equal to that big long equation. Now, we can divide through by r to the power of 40, and that will help get rid of a lot of stuff here. And when we do, we get r to the power of 60, 2r58 plus 14r56 plus 11r54. And then we get minus r to the power of 10 plus ar to the 6 plus br to the 4 plus c, just c by itself. All right. Now what I will do is I will put some of these on the other side. 2r58 minus 14r56 minus 11r54. And then the rest I will leave on the other side. So with the minus r to the power of 10 plus ar6 plus br4 plus c I will leave on that side, and I will concentrate just on those guys right there. From those guys I will factor out an r to the power of 54. When I do, I will get r to the power of 6 minus 2r fourth minus 14r squared minus 11. And then at this point, I will break up this r to the 6th into r squared times r to the power of 4. And that is done because we have an expression already for r to the 4th. It's right here. R to the 4th is equal to 3r squared plus 11. So wherever we feel that it will help, we can substitute it in. So r squared, let's substitute it in, r squared plus 11, like that. So 2r fourth minus 14r squared minus 11. All right, let's expand this now. We get 3r to the 4th plus 11r squared minus 2r to the 4th minus 14r squared minus 11. And then this becomes r to the 4th minus 3r squared minus 11. Well, look at this right here. And then look at this guy. That's equal to 0. Very helpful. So that means this is 0. This is therefore 0. So this whole expression we have just shown is 0. So that means that equation summarizes to just 0 is equal to minus r to the 10th plus ar 6th plus br 4 plus c. And that obviously is much easier to deal with. And what we can do is we can put the r to the 10th on the other side, and when we do, we get r to the 10th is equal to ar6 br4 plus c. Now we've got a lot of exponents here, so I want to utilize this finding that we have previously established right here, and the hope is that that will hopefully simplify things even more for us. But we've got to do a little bit of algebra here. The r to the 6th, anywhere we see that obviously can be broken up into r times r to the 4th, correct? And r squared times r to the 4th, well, r to the 4th, we have established that it's 3r squared plus 11. So if I expand that out, I get 3r to the 4th plus 11r squared. Okay, we can keep going here because r to the 4th right here, we know, is 3r squared plus 11. So keep going, and we get 9r squared plus 33 plus 11r squared, and that therefore is 20r squared plus 33. Okay, so that's r to the 6th. How about r to the 8th? that would be r squared times r to the 6th, correct? Well, r to the 6th we just established. We just got r to the 6th is that. So we can substitute that in. It would be r squared times 20r squared plus 33. And that is 20r to the 4th plus 33r squared. And again, we can substitute in r to the power of 4th being 3r squared plus 11 plus 33r squared. And that is 60r squared plus 220 plus 33r squared. And therefore that is 93r squared plus 220. Okay, now we can do one last one, which is r to the power of 10. That's going to be r squared times r to the 8th. And that's r squared times r to the 8th, which we have already established as being 93r squared plus 220. So that's going to be 93r to the power of 4 plus 220 times r to the power of 2. 93, well, r squared we have established many times was 3r squared plus 11. And then we substitute that in and expand. And finally we get 279 r squared plus 1023 plus 220 r cubed. And that is 499 r cubed plus 1023. Okay, so I think now we have enough to substitute into there. So r to the power of 10 is equal to a r 6th plus b r 4th plus c. R to the power of 10 I have just established as that. So let's substitute that in. 499 r squared plus 1023. A r to the 6th I have figured out was 20r squared plus 33. So let's put that in. And then b r to the 4th, well, r to the 4th we know is just 3r squared plus 11. And then we've got this lone c. All right, we are almost in the final steps here. So now let's put everything on one side and expand. So this would give me 20ar squared plus 33a plus 3br squared plus 11b plus c, and then bring those guys over, minus 499r squared minus 1023. Let's factor out the r squared, collecting like terms. So I got 20a plus 3b minus 499, and then the rest is going to be pretty much by itself, 33a plus 11b plus c, and this 1023 negative. Okay, so this plus this equals 0. R is not 0. R was established as some root. So that means the only way this can work is if this is 0 and this is 0. That's the only way this equation could hold true. So that means that 20a plus 3b minus 499 is equal to 0. So that means that is equal to 499. And then therefore 33a plus 11b plus c has got to be equal to 1023. So now what we have to do is come up with integer solutions by inspection, since we don't have enough equations here. We have 3 variables, we only have 2 equations, so we have to use some inspection. Well, this guy, b, we have to kind of say what could be the possible value of b for a to be an integer. Well, if I use a number, I've obviously got to make it so that what's left over is a multiple of 20. Well, if I try 19, it would become 480. That's a multiple of 20, but I would have to subtract 19, but 19 is not a multiple of 3. All right, how about if I bring it down to 460? That would mean I'd have to subtract 39. 39 is a multiple of 3. So as you can see, it's sort of just a trial and error at this point. So that means when b is 13, I get 20a plus 3 times 13 is 499. That would mean 20a is 499 minus 39, that would work because that would give me a value of 460. And 460 is indeed divisible by 20. It actually gives me a value of 23. All right, now I have to figure out the value for c. So let's see if I get an integer value, and I hope that I do, because I don't want to go back and do more trial and error. So I'm substituting the values of a and b into this, and let's see what we get for c. So this is 759, this is 143, plus c is equal to 1023. So when you do this math, you get c is equal to 121. Great, perfect. So I've got 3 values, and therefore I got my ABC. So the last step of this question, if you remember, was to figure out a squared plus b squared plus c squared. Okay, no problem. That'd be 23 squared plus 13 squared plus 121 squared. And that is 529 plus 169 plus 14641. And the sum of those numbers is 15339. 15339 is the answer to this challenging question, and that would be choice D. Okay, for each positive integer d and positive integer k, we use the symbol dk to represent the positive integer having exactly k digits, and each of which is equal to d. For example, 2, 1 is equal to 2, 3, 4 is equal to 3, 3, 3. There are n quadruples, p, q, r, k, with p, q, r positive digits, k a positive integer with k less than or equal to 2018. P2k minus qk is equal to rk squared. The sum of the digits of n is. So let's first start off with a simple example to help you understand what they're talking about. PQRK. For example, if that was 1, 2, 3, and 1, that was the quadruple. Then this expression would be 1, 1 minus 2 is equal to 3 squared. And that indeed works out. So that is how you would do this. So let's talk about dk in general. dk in general is the digit d a whole bunch of times. So basically d times, or k times I should say. Like that. Now we can factor out a d, and when we do, we get all ones. Like that. And this is k times. Now, if we factor out a 9, if you write 1 over 9 like this, you will get 9 d times. Sorry, k times. And then this d over 9 we can put by itself, but 999 is really 100 ... 00 minus 1, or we have 0 appearing k times. And then finally, it's d over 9, with this being 10 to the power of k minus 1. Like that. So, using this as the simplified expression for dk, we can get a formula for p to the 2k minus q to the k is equal to rk all squared. And here we go. So here's our expression, and every time we see one of these, we substitute this guy, this formula. So as you can see, for qk we put in this, and for P2k, instead of k, I just put in 2k, and then for rk, I just put in that formula, and don't forget to square it. And then you have to simplify it all the way down, and when you do, you end up with this expression. All right, so I'll let you do the simplification. So This is what we are now working with. And we now have to look at values of k. Well, k is less than or equal to 2018. And it is an integer, so obviously it's greater than or equal to 1. So we're going to look at three cases. We're going to look when it's equal to 1, 2, and then 3 to 2018. When k is equal to 1. Here, this expression, when k is equal to 1, when you substitute the value of k to be 1, it becomes this right here. And that can further be simplified to this, or 11p is equal to r squared plus q. Now, for each possible value of p from 1 to 9, we determine the possible values of q and r by looking for perfect squares that are at most 9 less than 11p. Now, the reason we have a boundary for p is because if you notice this expression, 11p plus, or rather is equal to r squared plus q. Remember, p and q and r, they're all just digits, right? They tell you that in the question. They tell you that p, q, and r are positive digits, and k is an integer. But p, q, and r are just digits, so they can only be from 1 to 9. That's where we get that from. So let's make a table. Let's make a p, q, r, and k. Well, k we know is 1 for all of these, since that is the whole case. So let's say what we get for p, q, and r. And this takes a little bit of time, a little bit of plug and play. So let's start with 1. When p is 1, you get the following solutions, 7 and 2. And I'll give you the solutions rather than talk you through them, because you're just kind of going through that formula. And those are the only ones for p equals 1. When p is 2, you get 6 and 4. When p is 3, the only one is 8, 5. And then when p is 4, you get 8 and 6. When p is 5, 6, 7. When p is 6, you get 2 and 8. And when p is 8, you get 7 and 9. So you get 8 here in total. 8 quadruples. Now let's proceed to k equals 2. K equals 2, we have the following scenario. When k is equal to 2, you take our formula and it becomes this. And when you simplify it, it becomes that. So, because p ranges only from 1 to 9, the only possible values of this 101p are these guys right here. And because r is a digit and it only ranges from 1 to 9, the possible values of an 11r squared are these. So we have to look at these numbers and see which of them differ by at most 9, because q, if you isolate it for q, it would be 101p minus 11r squared. And when you look at these values and see which one of them differ by at most 9, because q is from 1 to 9, the only ones that work out are these guys right here. And those ones, each of them, give the corresponding values of PQR, 1, 2, 3, 4, 8, 6, 7, 3, 8. So this gives us another 3 quadruples. Okay, so now we have graduated to the last case, and that is when k is between 3 and 2008 inclusive. So all of these will be talked about in one batch instead of going 3 and then 4 and then 5. So here is that famous equation that we were looking at. Now, first let's assume that we have to look at only this guy right here, this 10 to the k. Since k is greater than or equal to 3, then that means that it doesn't matter what this is going to be at least 1,000. At least, right? If k is 3, it'll be 1,000. So that means that this 10 to the k times this r squared minus 9p has got to be at least 1,000, so greater than 1,000 most likely. Okay, so now let's look at that side. P, Q, and R are digits, right? So let's look at the max and min. Max possible value for that expression would be 9 times 9 minus 9 times 0. Remember, we're trying to maximize, plus 9 squared, and that is 162. The minimum possible would be 9 times 0 minus 9 times 9 plus 0 squared, and that's minus 81. Okay, notice there's a bit of a contradiction here. So we're saying this is between minus 81 and 162. So since that equals that, essentially what we said was that this, which is 10k times r squared minus 9p, is between 162 and minus 81. But up here, we concluded that it's greater than 1,000, and that's a contradiction. If it's in this range, how can it be greater than 1,000? So that didn't work. So if that doesn't work, what does that mean? It means that we don't concentrate on this, we concentrate on that. The only way this is going to work is if r squared minus 9p is equal to 0. That's it. That's the only way this will hold true for this range for k. All right, let's work with that. So r squared is equal to 9p. So that immediately tells me that r is a multiple of 3. Since r squared is equal to 9p, because that means that r is equal to 3 times the root of p. So r is a multiple of p. So that means r, since it's a digit from 1 to 9, it can only be either 3, 6, or 9. Okay, so that's a pretty decent progress, I think. So let's see. Let's figure out what happens for r equals 3, r equals 6, and r equals 9. If r equals 3, this expression gives me that 3 squared is equal to 9p, and therefore p is equal to 1. Then I can substitute my value back into here. So I have 9p, which is 1, minus 9q, plus r squared, which is 3 squared, is equal to 0, because remember, this is 0. So that looks like 18 is equal to 9q, so q is 2. Okay, so we got one set here for PQRK. We got 1, 2, 3, and then k, where k is between that. Okay, so that's pretty good. Let's move to the next one, when r is 6. When r is 6, we've got 6 squared is equal to 9p, so that means p is 4. And then we substitute into this formula, just as before. So we got 9 times p, which is 4, minus 9q, plus r squared. R is 6, so 36 is equal to 0. So that means we will have 72 is equal to 9q, and therefore q is equal to 8. All right, so now my quadruple is PQRK is 4, 8, 6, and k. Okay, let's try r equals 9. By now you're an expert, so this would be 9 squared is equal to 9p, p is equal to 1. And then therefore 9 times 1 minus 9q plus r squared. 9 squared is equal to 0. So that means, sorry, p is 9, not 1. So this means that if you solve for this, it would be 9q is equal to 81 times 81 plus 81, which is 162. So that means q is 18. But remember, q has to be a digit. And therefore, since this is not a digit, this doesn't give me any solutions. So the only solutions I got was this and this. And if you remember, k was between 2018 and 3. So for this, we can have 1, 2, 3 for values of p, q, r. But k, we have a range, and that is 2016 values, right? From 3 to 2018. So we got 2016 possible values. So we have 2016 quadruples here. It would basically be 1, 2, 3, 3, 1, 2, 3, 4, 1, 2, 3, 5, and so on. In a very similar way, P, Q, R, K here, we have the same sort of story. We have 2016 values for K. So again, another 2016 quadruples. Each quadruple is of the form 486K. So 4863, 4864, and so on. Okay, so let's count up all our quadruples. 2016, plus we had 3 here, and then we had 8 here. So 2016, 3, and 8. 2016 plus 2016 plus 3 plus 8, that is the total number of quadruples, and that is 4043. So that is equal to n. There are n quadruples. We figured out n. Now they want the sum of the digits of n. Sum of the digits of n, 4 plus 0 plus 4 plus 3, and that is 11. So number 25, very challenging question, very time consuming, is C. Angle QRS, point T is on QS with angle QRT equal to angle SRT. Suppose that QT is M, TS is N for some integers M and N with N greater than M, for which N plus M is a multiple of N minus M. Suppose also that the perimeter of triangle QRS is P, and that the number of possible integer values for P is M squared plus 2M minus 1. The value of N minus M is. Let's do some labeling. Let's call this side RQ equal to X, and this side RS equal to Y for now. The very first thing is I've got to label this theta and this theta. So immediately, since that line RT cuts that in half into 2 equal angles, I immediately think of the angle bisector theorem. And that is going to give me as follows: x over m is equal to y over n, directly from the angle bisector theorem, no tricks at all. And then I think I'd like to put the m and the n together, so m over n is equal to x over y. Well, if that is the case, then that's very helpful because I can call x and y in terms of m and n. So x could be some multiple of m, and y could be some multiple of n. As you can see, the k's would cancel, and it would just give me m over n. So y I'm going to refer to as kn, and x I will refer to as km. Now, we are going to use something called the triangle inequality, which I'm sure many of you know. Two sides have to be greater than the third side. So let's see here. I will compare this side and that side. So that's x and y, so x plus y has to be greater than the third side, which is right here, which is m plus n. And instead of putting x's and y's, I'm going to put the km plus the kn values greater than m plus n. Factor out the k and you get m plus n is greater than m plus n, and that basically means that k is greater than 1. Now I will use the triangle inequality again, but this time two different sides. I will compare this plus this to be greater than the third side. So it would be x plus m plus n is greater than y. Well, again, instead of x's, I'll put km plus m plus n, and then instead of the y, I'll put the kn. So this becomes m plus n is greater than kn minus km, and I can factor out a k, and when I do, it will be n minus m, and I'll just bring that into the denominator. So k is greater than n minus m plus n over n minus m. All right, so that's pretty decent, I think. Now let's start talking about the perimeter, which is something they are putting a lot of emphasis on in this question. The perimeter of this triangle, just based on what we have up there, is x plus y plus m plus n. And the perimeter in terms of k's and m's, x is km, y is kn, and then this is m plus n. And I think I can factor out something. I can factor out the k. This will be m plus n. This will be m plus n. Factor out the m plus n, and I get k plus 1. All right, so now let's discuss this. We have some very helpful inequalities up here. The first one tells me that k is greater than 1. So since k is greater than 1, that means that the perimeter must be greater than m plus n times 2, because k is greater than 1, so that has to be greater than 2. So therefore the perimeter's got to be greater than 2 times m plus n. Also, another thing that we know, that p is an integer. So since p is an integer, p has to be at least, so greater than or equal to this plus 1. So 2 times m plus n plus 1. So for example, if this was whatever, 12, and p is greater than 12, p has to be at least 13. And that's all that is, really. Nothing too complicated. All right. Now let's talk about this inequality. Since k is less than m plus n over n minus m, that means that this can be looked at in a very kind of similar way, that's equal to p. So that means that p is less than m plus n times this. We're going to substitute for that. So it would be m plus n over n minus m, and then don't forget about that plus 1. And in a very similar way, since p is an integer, p has to be less than or equal to m plus n times that m plus n over n minus m plus 1 minus 1. So for example, if this was, say, 14 and p is less than 14, p has to be at least 14 minus 1, which is 13. So that's why we put in that negative 1 there. Okay, well, these two things, this one and this one, give me a range. Combining, it gives me a range that p is between. It's either less than this guy, p m plus n times m plus n over n minus m plus 1 all minus 1, or it's greater than this guy, which is just 2m plus n plus 1. Okay, so for example, let's say the numerical values were 50 and 25, and I asked you, they're all integers. How many values does p have? Well, they're all the integer values from 25 to 50 inclusive. So the total would be, 25, 26, 27, all those guys. And you'd easily calculate that by doing 50 minus 24. So in the same way, if I said, how many integer values are there for that range? it was the same thing. You take this and subtract from it this, and then subtract one more. Exactly how I did there. So the number of values of p would be this guy, which is m plus n times m plus n over n minus m plus 1 minus 1 minus this guy, 2, let's just put it in brackets, m plus n plus 1, and then don't forget to subtract 1. So minus 1. Exactly like I did for this right here. And then they told me that the number of values of p is equal to something in the question. The number of possible integer values for p is this, m squared plus 2m minus 1. So that m squared plus 2m minus 1 is essentially what this whole thing is equal to. So I'll put it here. M squared plus 2m minus 1. And there you go. This is what we have to now simplify. And there you go. There's a simplification. I don't think you want to hear me go through all of this. That would be very painful. I encourage you to do this on your own. And when you do, you get to this very nice result at the very end. That 0 is equal to m times n minus m minus 4. Well, m and n represent distances, so m obviously cannot be 0. So that means that n minus m minus 4 must be equal to 0. That means n minus m is equal to 4. And that is what they wanted you to figure out, the value of n minus m. It's 4, and therefore the answer to this challenging question is A. 3 real numbers x, y, and z are chosen randomly and independently of each other between 0 and 1 inclusive. What is the probability that each of x minus y and x minus z is greater than negative a half and less than a half? Let's draw at the x, y, z axes and a diagram. This is, of course, the x-axis, and this is the y-axis, and this is the z-axis. Our boundaries, of course, are 0 to 1 for everything, so that's 0 to 1. This is obviously 0. Here's 1, and here's 1. Now we take into consideration our restrictions or conditions. So the first one is that x minus y is between negative a half and a half. And the second one is that x minus z is between a half and negative a half. So let's draw these. First, let's look at this inequality. So that basically would mean that y is less than x plus a half. And we can quickly draw that. X plus a half. So for example, when x is 0, we're really just looking at the xy plane now. When x is 0, y is a half, so approximately here. When x is a half, y is 1, so approximately here. And then we can connect those two lines, and let's do that. So here we go. So remember, we're just looking at the xy plane right now. Later we'll look at it with the z-axis. Now let's look at this part. That would basically mean that x minus a half is less than y. So again, let's plot that. When x is, say, a half, you're going to have a 0. So that's going to be approximately x minus y less than a half. So for example, when x is a half, y will be 0. So that's right here. When x is 1, y will be a half right here. And then connect those lines as well. So as you can see, we want the area that is in between those two lines, because y's got to be less than this and it's got to be greater than that. Okay, that it's a cube, so that's going to be extrapolated all the way to the other side. So that's the key in this question, that you've got to be able to figure out the three-dimensional aspect of it. So we have to connect this, so let's do so all the way to the other side. So there we go, and then I join them all. So that basically means that we've sliced off a section of each side, as you can clearly see. I hope this is drawn in a way that you can see that. Now that part is actually pretty straightforward, because all I have to do is just really look at the XY plane, and I'll draw the XY plane here, let's say. And you don't even need that big of a diagram, just something like that is sufficient. And then really what I did is I just chopped off corners like this. And you can easily figure out the volume of that. So the entire cube or face is 1 times 1. And then I chopped off this guy and I chopped off that guy, because that falls outside of our boundaries that these inequalities create. So this one would be a triangle, 1/2 base times height, 1/2, 1/2, and 1/2. And then similarly, this is also a triangle, 1/2 base times height with the base of a half and the height of a half. So this is 1 minus an eighth plus an eighth, which is a quarter. So 1 minus a quarter, so 3/4. But that is just the shape that basically is 2D. We want the 3D version. Well, the 3D version, to get the volume, all you have to do is just multiply by the height. And the height from there to there is just 1, because it's 1 on the z-axis. So you take that 3/4 and you just multiply by 1 to get the volume of that shape. And that, of course, just gives me 3/4. So this 3/4 is a very important part of the question. We'd be done if there wasn't another inequality. But we do have another inequality, and that is x minus z now has to be between a half and negative a half. Okay, in the same way, let's plot this. So this gives me two equations. The first one it gives me is that x minus a half is less than z, if I'm looking at that one. And then if I'm looking at this one, it will give me that z is less than x plus a half. And in a very similar way, let's plot those. So this time it's the z and the x-axes. So when x is a half, z will be 0. So that's going to be right here. And then when x is 1, z will be a half. So that's approximately here. So we just connect those from there to there, approximately like that. And then this one here, when x is 0, it'll be a half for z, and when x is a half, it'll be 1. So again, we're connecting it like that. So as you can see, in a very similar way, we have chopped that into an area, and we of course have to just look at that section. So let me draw the same thing on the top. So that's going to be approximately here to here, and from here to here. And let's now connect those. So we're connecting it to kind of show what happens. So there we go. All right, so I think that's pretty decent. All right, so now we have to figure out what's going on. Well, the first part, right, we figured out was 3/4, and that's great. But now from that 3/4, I have to cut out these shapes. And this shape, this is one of the faces, along with this right here. I'm chopping that off. So I hope that makes sense. I'm chopping it off from that side, and I'm chopping it off from this side, because we can only keep what's in the middle because of these inequalities. So, all right, not a problem, right? You just take this and then subtract from it those two shapes. But it's not that simple. Why? Because those two shapes also have this part missing, as you can see there. So it doesn't become that easy. So let's rationalize this. The first thing, of course, was we take our 3/4, which is what we got. And then from that, we have to subtract something. And that something, of course, is this triangular prism, right? That's what this is. And there's two of those guys, so I have to subtract those two triangular prisms. So 2 TP triangular prisms. But before we subtract the triangular prism, we have to subtract this segment of it. This segment that is not part of the triangular prism. See what I mean? And that is actually a square base pyramid. Square base pyramid. So that square base pyramid, I think that's the most challenging part. I think most people can get to here, but then it becomes challenging as to what is this shape right here. So let's illustrate that. Let's talk about that a little bit before we do this calculation. So we have this triangular prism, right there. And what we did was we take that triangular prism and we put it here because we have to subtract that from the 3/4. No problem. But there is a problem because we then have to slice that, as I tried my best to illustrate here in the diagram. And that's what this does. It slices that triangular prism. And when you do, you get left with this shape. Now, what is that shape? That is the square-based pyramid. As you can see, this is the square base, and the rest of it is in the shape of a pyramid. So now we can figure this out. So this is 3/4 minus 2. The triangular prism, the area is up here, the big one. That is the triangle, and then this is the height all the way down. It's the area of the triangle, which is 1/2 base times height. The base is 1/2, the height is 1/2. So 1/2 times 1/2 times 1/2. And then you multiply that by the height, top to bottom, which is a 1 in this case. Okay. The square base pyramid, this guy, which is where that slice occurs right there. Above the slice, we have to get rid of that. How do you figure out that area? Well, the area of a square base pyramid is 1/3 times the base times the height. So 1/3 times the base. The base is a square. That's why it's called a square base pyramid. And the dimensions of that square are 1/2 and 1/2. So the area would just be 1/2 times 1/2. And then the height is from here to here, and that is also 1/2. So that is also 1/2. So there we go. We have this question done. Now all we have to do is just figure out that math. So that's going to be 3/4 minus 2, and that looks like 1/8 minus 1/24. Okay, so 3/4 minus 2, that is, get common denominator, 3 and 3, 3 minus 1, so 2/24. And therefore this is 3 minus 4 over 3 over 4 minus 4/24. And that looks like we can just get a common denominator. Multiply top and bottom here by 6. So that'd be 18 minus 4/24. That is 14/24. In lowest terms, 7/12. 7/12 is the answer. I encourage you to, and I'm being serious, get some Play-Doh. And Play-Doh, or sometimes it's referred to as plasticine, you can get these at any kid store, toy store, and then just make shapes. And then take a knife and cut through them. And I promise you that will help you, because sometimes it becomes very difficult to visualize it. Or if there's some computer software, perhaps that might be even better. So 7/12 is the answer to number 25, and that would be B. Positive integers such that x is less than y is less than z, and x, y, z is equal to 2 to the power of 2, 3 to the power of 2, 5 to the power of 2, 7 to the power of 2, 11 to the power of 2, 13 to the power of 2, 17 to the power of 2, and 19 to the power of 2. When n is divided by 100, the remainder is. This question has a long way and a short way. Obviously, I'm going to show you the short way. The long way would take an hour. We had to actually list all the triples and Oh, actually, that's not even the long way. The long way is when you look at each individual scenario, but we can combine them. So we have A, B, C, right? So let's just talk about 2. How do I place the 2's? There's a few ways, right? You can put a 2 here, or you can put a 2 here, and then this would be a whole bunch of other terms without the 2's. Or you can put the 2's here with A not having any 2's in it. Or you can put the 2's here with B not having any 2's. Or another way is to combine the 2's, where A would have both 2's, or B would have both 2's, or C would have both 2's, like that. So as you can see, there's 1, 2, 3, 4, 5, 6 ways of placing the 2's. And in a very similar way, there's 6 ways of placing the 3's. And 6 ways to place the next prime factor, which is the 5's, and so on. 6 ways to place the 7, 6 ways to place the 11, 6 ways to place the 13, 6 for the 17, and 6 for the 19. So in total, we have 6 to the power of 8 ways that we can combine all of these numbers. So you think, okay, that seems to be like a very big number, and it is 1679616. Now, that is not the right answer. That's the total number. The reason it's not the right answer is because you have a whole bunch of doubles in here. We've got a lot of numbers that we've counted twice. So we have to subtract those from this big total number. Okay, so now let's chase the doubles. We now have to eliminate overcounts. I think overcounts is a better word to use. Okay, so what do I mean by overcounts? Well, for example, if we had 2, 2, and 3, and then we had another 2, 2, and 3, as you can see, those are the same. And we want unique triples. They didn't put the word unique there, but that's what they really mean. Well, overcounts can happen in a few ways. The first is where x is equal to y. So these were my triples, right? X, Y, Z. And as you can see, this is a scenario where x was equal to y. Okay, so if x is equal to y, and I have some sort of a triple ABC, and this is x, and this is y, and x equals y, then you'd have this kind of a scenario. Okay, so let's be consistent and let's just use the ABC like I did here. It doesn't really matter what letters you use. Okay. So first scenario number 1, A is equal to B. That would give you a whole bunch of doubles. So now again, we're going to look at these prime factors and figure out how do we place them. So again, let's just talk about 2, just like how we did in the first one. We can put 2 here, and here C would be some other, number. Or we can put 2 times 2 here, and then these would be the same. So same, whatever they are, same and same. So these are 2 ways of arranging the 2's, as you can see, 1 way and 2 ways. So 2 ways for the 2's to make A equal to B, correct? And in a very similar way, you'd get 2 ways to arrange the 3's, and so on, ... 2 ways to arrange all the primes until 19. So in total, it would be 2 to the power of 8, right? 2 here, 2 here, 2 here, 2 here, all the way. 2, 2, 2, 8 times. So that's how many ways you could get A equal to B. But there's also a scenario of B equals C. And that would give you another 2 to the power of 8. And then there's also a scenario where A equals C. And that would give you another 2 to the power of 8. So these are the total overcounts. So that's basically 3 times 2 to the power of 8. Okay. So basically now we have the scenario where 6 to the power of 8 minus the overcounts, which is 3 times 2 to the power of 8. Okay, are we done? No, because we are given a very specific condition, which I hope you don't miss, which is that x has to be less than y, it has to be less than z. And that condition, therefore, has to be utilized to modify this. X has to be less than y, it has to be less than z. And this happens 1/6 of the time. Of all the triples, 1/6 of them will satisfy this inequality. So then you have to take this and multiply it by 1/6. So 6 to the power of 8 minus 3 times 2 to the power of 8. And that would give you the correct answer. And that is 279,808. And they're saying that once you get this answer, they want you to divide by 100 and then get a remainder. Well, obviously, the remainder is going to be 8. So then question number 25, the answer is 8, which is choice C.